Okay, so let's start the first morning session of second day. So the first speaker is Patrick Lal from the University of Texas and Austin. So please start.
Hi, good morning, everyone. Thank you very much for the introduction. Thank you very much to the organizers of the conference, and thank you for coming to my talk. So I'll jump right in. So I'm presenting a new, faster algorithm for coherent phase estimation and coherent energy estimation. So what is the task? We're given as input a unitary with eigenvalues e to the 2 pi I lambda j, or a Hamiltonian with eigenvalues lambda j. And we're also given an input state, which is some unknown superposition of the energy eigenstates of our unitary or Hamiltonian. And our goal is to compute into an ancillary register an estimate of the corresponding eigenvalue. Now, this is commonly known as phase estimation, a very important subroutine in many quantum algorithms. In particular, the quantum metropolis algorithm is an important application of this, as well as some algorithms for partition function estimation and Bayesian inference. And really the only way this could be done in the past is using textbook phase estimation. So applying the unitary several times, then running the quantum Fourier transform, and doing this and collecting many estimates of the estimate lambda j, and then running a quantum sorting network in order to perform median amplification. So this is actually a very complicated method, and I was hoping in my work to improve on this method. So the technique that I'll be using to improve on it is block encodings. Block encodings are a novel method for designing quantum algorithms, and they basically give you the capability to manipulate non-unitary matrices on a quantum computer. Probably an excellent reference for this work is this work by Gillian, but there's also this recent review article by Martin et al. That came out a couple months ago. That also features an independent discovery of the phase estimation algorithm in our work. The basic idea is to take any matrix and just tuck it into the top left corner of a unitary matrix. And then we have all kinds of primitives that let us manipulate block encoded matrices. So obviously we can take a quantum state and multiply it by a block encoded matrix. We can take products and tensor products. But we also get to take linear combinations of block encoded matrices, as well as apply polynomials to the singular values of our matrix. So this, in particular, this last step, singular value transformation, is particularly important to our algorithm because it has a very low ancilla cost. So how does our method actually work? So we introduce a new tool. Say you are given a block encoding of some projector pi, and you want to measure in, say, another qubit, compute into another qubit, whether or not you're in the 1 eigenspace or in the 0 eigenspace, which is performed by this isometry here. So this block measurement lemma essentially shows that if you have an approximate block encoding of a projector, there is a quantum channel that implements something very close to this isometry. So now if we have a projector, we can if we can just construct a projector, we can turn that into a qubit. So the actual algorithm involves designing projectors whose eigenvalues indicate the kth bit of the eigenvalue lambda j. And we can make these projectors using singular value transformation. So we apply a singular value transformation lets us apply polynomials to the Hamiltonian. So we simply must find polynomials that are very close to indicating the kth bit of the input lambda. So ideally, we would like our polynomials to look like this. For the least significant bit, it oscillates between 0 and 1, and it jumps instantaneously between the two. And for the more significant the bit, the slower the rate of oscillation. However, no polynomial looks like this. Polynomials are continuous functions, but these functions are pretty discontinuous. So in order to get this to work, we need to essentially assume that certain eigenvalues are not possible. That whenever we are around one of these jumping regions, there's simply no eigenvalues there. So now the polynomials have these little gray regions which is enough room for them to move from close to 0 to close to 1. In fact, we can make these regions even wider. The cost of singular value transformation is proportional to the degree of the polynomial, and jumping very quickly from 0 to 1 requires very high degrees. So if we have more room to interpolate, that makes the algorithm faster. So by subtracting off the less significant bits, so we calculate the less significant bits first and then subtract them off the eigenvalues later, we can actually widen these gaps because we can guarantee that no eigenvalues are present here. So these are essentially the stencils, the polynomials that we like to craft. How do we actually make polynomials that look like this? Well, we can start by making polynomial approximations to the cosine function. So just from Hamiltonian simulation literature, we have very good polynomial approximations for cosine and sine. So by taking these and shifting and scaling them appropriately, we can make cosine functions that indicate the bit that we would like. Now all we need to do is take values that are greater than 1/2 and push them up to 1, and take values that are less than 1/2 and push them down to 0. There also exist polynomials for doing this sort of thing in the literature. So if we combine these polynomials together, we get the desired polynomials that look like this. So that essentially describes the whole algorithm. Let me talk briefly about the performance. So there are really 3 parameters for this. There's the precision, the number of bits that you would like, the number of bits in your estimate, the probability with which you would like your algorithm to succeed, so 1 minus the failure probability delta, as well as the gap parameter. So remember, we had to assume that certain eigenvalues are impossible. What fraction of the range of eigenvalues are we excluding? That's parameterized by alpha. Phase estimation was already asymptotically optimal in terms of all of these parameters, and so is this new method. So the improvement is entirely in terms of ancillas and in terms of constant factors. So in particular for the ancilla cost, phase estimation required us to make many estimates and then run a quantum sorting network onto them in order to perform amplification. That means that the number of ancilla we need actually scales with the accuracy. But this is not the case in the new method because all the amplification is just being done by these polynomials, and singular value transformation does not need more ancillae for a higher degree polynomial. As for the query complexity, so just measuring how many times we had to apply our block encoded Hamiltonian, of course, in reality, this is going to depend on your situation. But for this analysis, I found that if for sufficiently large n, sufficiently small alpha and delta, the speedup stabilizes at around 14x for unitaries if you're doing phase estimation, or around 20x if you're applying this to a Hamiltonian and doing energy estimation. So thank you very much. I'd be ready for questions now.
Okay, thank you very much for your talk. So any question or comment? So you can raise your hand, or you can write your question in a Q&A system. Okay, so there is one question from John. Can you see this? What should I read?
I can pull it up. Yes, I can see it.
Okay.
In slide 9 for the second digit. Starting from the bottom, it looks like you'd be closer to 1, 0 by slightly shifting the curve. Right. So what is happening here is that whenever we perform a polynomial approximation to for this amplification function, the function that takes small numbers and makes them close to 0, and large numbers larger than 1/2 and makes them close to 1, you see the polynomial overshoots a little bit. Unfortunately, for singular value transformation, we can only run polynomials. We can only perform polynomials that are bounded between 0 and 1, or -1 and 1 rather. So in order to correct that, we have to smush our polynomials down a little bit. But this is fine. The error that we incur from this is bounded by delta, and the degree scales like log 1 over delta. So we can make this overshoot. This overshoot is easy to suppress.
Okay. Any question? So if not, because it's time, so let's move on to the next speaker. Thank you for your talk.
Thank you very much.
So the second speaker, could you share your slide? Okay, I can see your slide, but this is not a presentation mode. Okay, so
can you see my first slide? And can you hear me?
Yes, yes. So the next speaker is Seiichiro Tani from NTT. So please start.
Thank you for the great introduction. And I'm Seiichiro Tani. I'll talk about quantum algorithm for finding the optimal variable ordering for binary decision diagrams. You can get you can get the full version at archive here. Let me first introduce a central concept in this talk. An ordered binary decision diagram, in short, OBDD, is a graph representation of a Boolean function. For instance, if f is a function like this in a product function, the OBDD for the function f is like this. And this is a directed acyclic graph with a single root and two terminals. And every path from the root to leaf corresponds to an assignment to the Boolean variables. For instance, if x4 is 1 and x3 is 0 and x2 is 1 and x1 is 1, then you can get the function value true. And basically, the OBDD is a compressing form of the binary tree representation of a Boolean function. And OBDDs have many useful properties. So this has been extensively studied in both theoretical and practical fields, such as VLSI design, formal verification, and combinatorial problems problem learning. And for details, see the standard books, some textbooks, like recent issue of The Art of Computer Programming by Professor Knuth. And one of the most crucial problems in using OBDD is how to find a minimum OBDD for a given Boolean function. This is a very difficult problem. Actually, this was proven to be NP hard, and trivial enumeration-based algorithm works in about n factorial time. So let me define the most important concept in this talk. Variable ordering, which is reverse ordering of variables to be read. For instance, in this OBDD, the ordering of variables to be read is x6, x4, x2, x5, x3, x1. So the variable ordering of the left OBDD is x1, x3, x4, 5, 2, 4, 6. So as you can see, OBDD size depends on variable ordering. So then how much can variable ordering affect OBDD size? Actually, the size of OBDDs can change exponentially depending on variable ordering. So this implies the time required for OBDD-based operations such as equivalence check and logical operations on OBDDs can change exponentially. Sorry. So it has been central how to find the variable ordering for minimum OBDD and how hard it is. So for instance, this is a generalization of the function we just saw in previous slide. For one variable ordering, the size of OBDD is linear in n as a number of variables, and for the other, the size of OBDD is exponential. Actually, this is not a rare phenomenon. We can easily encounter such instances. So this is the following problem is very important. For given representation of Boolean function f, such as CNFs, DNFs, circuits, and OBDDs. And our goal is to find the optimal variable ordering. That is a variable ordering that minimizes OBDD representing f. There is a previous work that provides a classical algorithm that is much faster than trivial one. This is a 3 to the n time classical algorithm invented by Friedman and Sapowitz 30 years ago. This is only known algorithm with non-trivial complexity bound. We should note that the 3 to the n is much less than the time complexity obtained by trivial algorithm plus global search, which is square root of n factorial. Our result provides a quantum algorithm that is much faster than this previous algorithm. And our algorithm is a quantization of classical FS, Friedman-Sapowitz algorithm, which is based on dynamic programming. And there is some similarity in structure to Unbind et al.'s algorithm, which was presented at Soda conference. But there are some unique technical difficulties. First, it is unclear how to divide the problem into some small subprograms, unlike many graph programs. So we prove a new classical lemma by which we can divide the problem into small subprograms. But some programs are not scaled down versions of original problem actually. So we need to provide the algorithm with parameters so that it works for different kinds of subprograms. And these different kinds of subprograms have different time complexity. So we need to optimize by taking this difference into account. Finally, let me announce some correction in my long talk slide. Here, K-1, these should be K. Okay. So thank you very much.
Okay, thank you very much for your talk. Any question or comment? So, okay, please talk, Seb.
Hi, Seijiro, can you hear me?
Yes, I can hear you.
Great. Just a quick question. So yeah, you mentioned this connection to Andres et al.'s general approach for these dynamic programming. Is there a more general theme you see emerging here? I mean, when this kind of divide and conquer might be useful? I mean, it seems like your approach is also based on dynamic programming, just the recursion is different, right?
Yes, actually, our algorithm heavily depends on the property of OBDD. So I don't know how to apply the my idea to the other applications, but our problem is basically optimizing or finding a optimal permutation. So it might be possible to apply the our idea into the problem related to the finding optimal permutation, like optimal linear arrangement problem.
Okay. Thank you.
Okay. Any other question or comment? So the input of your algorithm is BDD, and how this is encoded? So,
when input is OBDD, then we assume the some some program outputs some OBDDs. Then we want to optimize the OBDD. So we think that such a situation when input is OBDD, but our algorithm allows other representations such as CNF or DNF or circuit as input.
So you assume the size of description of input is polynomial, or your time complexity is a function of input size?
That should be, the size of input should be ranging from the polynomial to exponential. So I don't know that because the size of input heavily depends on the representation. So we measure the complexity by the number of variables.
Okay, thank you. So any other question? So if not, let's thank the speaker.
Thank you very much.
So the next speaker, could you share your slide?
Yes.
Okay,
So,
I can see your slide. So the next speaker is Kaspars Barodis from University of Latvia. Okay, so please start.
okay, so thank you for introduction, and thank you everyone for attending. I will talk about flow function is small range, and this is a joint work with Andris Ambains and Jan Siraits. So about the problem, let me just remind you that in element distinctness function, we are given a function and we want to determine if there's a collision two inputs which gives the same output. And flow is a similar problem, but we are given two functions and we have to find a collision among them. Input one input such that the value of one function is the value of the other input of the other function. And we denote the size of domain by n and the size of range by k. And we are interested in quantum query complexity for this flow problem. And we want to minimize the number of queries. So we assume that the values of the functions can be accessed via queries to an oracle, and we want to make as few queries as possible. So as here seen in example, we have to find either a duplicate, or in flow, we have to find matching entry from one side to the other side. So, and these problems are long known, and there are well-known matching upper and lower bounds at n to the power of 2/3, provided that k is at least n. And of course, for element distinctness, this is the smallest non-trivial k, because if the range is smaller than domain, then obviously there will be a collision. But this is not the case for flow. The case when k is at least 2 is still interesting, because we can have equal elements on one side and equal on the other side, but we have to find a match between them. But this problem had not been researched very much. There was only trivial bounds known, and also there's a simple algorithm from Grover's search. And we explore this problem, and we give a non-trivial lower bound and a non-trivial algorithm. So the lower bound is based on a composition with a p-search problem, and in p-search we are just given a list of blank elements, and one element is non-blank, and we have to return the value of the non-blank variable. And for p-search, the composition theorem holds, which is what we are using. And basically, the reduction is, as can be seen here, we compose flow of k to k with p-search. We get this picture here, and basically you can see that this value is actually the same as flow of this larger instance. So we get the lower bound from this composition and reduction. And for the algorithm, let me quickly sketch it. We sample a few elements from each side and query their values. And we have these values. We check whether there's a matching element on the other side for one sample and for the other. And if not, then basically we are left with this situation where we can essentially discard these elements and consider this as a smaller instance of flow on smaller number of elements. And then we can solve it with a regular flow algorithm. Of course, we cannot access these elements directly. We do it via Oracle, but basically it works out to this complexity. And we can improve it by using not the n to the 2/3 algorithm for the smaller instance, but we have some better algorithm, either the trivial or recursively the same algorithm. And then we can improve this complexity to this line here. So we gave this algorithm, this lower bound, and we still have a gap between them. So that's an open problem. If we could show that this the lower bound holds here as well, then it actually would coincide with the algorithm bound, and it would imply better lower bounds for some other problems. Okay, so, thank you for attention.
Okay, thank you for your talk. So, any question or comment? So here you consider crow, finding crow, but what happens if you consider such as second pre-image, for example?
You mean sorry, can you explain in more detail what you mean by
so one pre-image is given and your task is to find another pre-image. So crow is you have to find two pre-images, but second pre-image is just one of two crows is given, and you have to find the other crow.
No, we haven't thought about that. I think that's something we have to think about. Maybe.
So there is one question in Q&A system. Can you see this? So did you try polynomial method to obtain a lower bound?
Basically, it's a bit hard to use a polynomial method here because for element distinctness, the good thing is that the elements can be permutated as you like, and then you can permute the polynomial and get a lower bound using that. But in Flow, we cannot use all permutations because we have to fix which elements are on one side and which are on the other side. So maybe with some smarter approach, it's possible, but it's not so easy to apply.
Okay, so any other question? So if not, let's move on to the next talk. So thank you for your talk.
Thank you.
So I can see your slide, but this is not in the presentation. Okay, so now I can see your slide. So the next speaker is Yashine Hamoudi from IRIF and Université de Paris. Okay, so please start.
Thank you. So I would like to give you an insight about the results I obtained with my co-author, Frédéric Magnus. And it's about quantum time-space trade-off for finding multiple collision pairs. Okay, so our result is about lower bound in a model that combines the quantum query model, so you can access the input with quantum queries, and also the space-bounded model, meaning your algorithm have a limited amount of memory. It cannot store all at once in memory. And here I just focus on the particular case of our result where the memory is limited to log n qubits. Okay, so the input is a vector x of size n, and you can perform quantum queries to this input, but you cannot store more than log n qubits of information. And so there are a few results which are known in this model for solving some problem, and I would like to list a few of them. So the first one is about finding the minimum in a list of n numbers. So classically, you have to do n classical queries to solve this problem with a small memory. And quantumly, it turns out that you can do better. You can do only square root n quantum queries. The algorithm is the famous algorithm from Dur and Hoyer. And the lower bound is the lower bound for Grover search. So a more interesting case is for the sorting problem, where you want to sort the n coordinates of your input. And when the memory is limited, classically, you cannot do an efficient n log n algorithm. The best you can do is n square, classical queries. And in the quantum setting, it was shown that you can, again, do slightly better. With log n qubits of memory, you will need to perform n to the 3½ quantum queries. And the lower bound for this problem, which is the most interesting part of this result, was shown in 2007 by Klauk, Spalek, and de Wolf. And in our paper, we studied a third problem, which hasn't been studied before, which we call the collision pairs finding problem. I will define what it is in the next slide. But for this problem, classically, it was known that the best you can do is n to the 3½. So the algorithm is some variant of the polar row method. It's called the parallel collision search algorithm. And the classical lower bound actually was shown by Dinour last year at Eurocrypt. And in the quantum setting, nothing was known. And what we're able to show is a lower bound, which is shown in red, and which says that for solving this collision pairs finding problem, you have to perform at least n to the 4/3 quantum queries. So there is still a gap between this lower bound and the best algorithm, which is a classical one, but at least it gives you a non-trivial result because it is superlinear in N. Okay, so let me define what is this problem. It's pretty simple to understand. It's about finding collision pairs in a random function. So a collision pair is just a pair of two values which are equal. So this is an example on this particular input. X2 and X11 are a collision pair because they are both equal to 4. This is a second possible collision pair. And in the problem we studied, the goal is to find many collision pairs. Let's say you want to find half of all the existing collision pairs. So more formally, we have a uniformly random input, x1 up to xn. Each coordinate is between 1 and n. And let's say you want to find n over 8 collision pairs. And if you do some basic computation, you'll see that for such a uniform distribution, there is a linear number of collision pairs with high probability. Okay, so it's possible to solve this problem. And it's an important problem, in particular in cryptanalysis. I have listed a few applications. And notably, finding many collision pairs is important for performing meet-in-the-middle attacks. And maybe if you attended the open question session yesterday, you remember this question by Scott Aronson, which is about finding a query space trade-off for the collision problem. So it's very related to the question we studied, but it's for finding just one collision pair. Whereas in our case, we are interested in finding many collision pairs, not just one. And actually, we were able to also prove a connection between the two problems, which is that any improvement to our lower bound, which is n to the 4 over 3, any improvement would give a non-trivial result for the collision problem. Okay, so I would like to give you just one slide about the technique we used. And we use a connection, which is well known, between proving time-space trade-off lower bound and the small success probability regime. And this is a result that, the main result we proved, which is that if you try to find just a logarithmic number of collision pairs with a very small success probability on the order of 1 over n, then you must use at least n to the 1/3 quantum queries. Even if your memory is unlimited, you must use those number of quantum queries. And this is the main result that you have to show, because using this result, there is a standard technique that gives you a time-space trade-off when the memory is limited. And the way we prove this result is rather different from what is done, for instance, in the paper of Klaus, Spalek, and De Wolf. We didn't use a polynomial or the adversary method. We used a more recent technique, which is called the recording technique, which was introduced by Mark Zandri in 2019. And we modified this technique a bit. We improved some part of it. And it allows us to prove this result. And as a byproduct, we also obtained a simpler proof of the quantum time-space trade-off for the sorting problem. And okay, so let me just conclude with this slide. Actually, the result we obtain is a bit more general than just for the case of log n qubits of memory. We handle also different possible size of the memory, and for each possible size, we have a lower bound in terms of the number of queries you have to perform. And yeah, that's it. Thanks.
Okay, thank you very much for your talk. So, any question or comment? You can raise your hand, or you can use the Q&A system. So there are two questions. Can you see this?
Yeah, I can see them. Yeah, so first question is, why did we choose n over 8? Okay, we could have chosen another constant. Like 1 over 8 is a larger constant we can handle in our lower bound. Yeah, it is a larger constant we can handle. But anything which is smaller than 1 over 8 would also give something meaningful. And so the second question is, what about an upper bound? So we also describe an upper bound based on a generalization of the algorithm of what's it called? Yes, the collision finding algorithm, we have some generalization of it to find an arbitrary number of collision pairs. But okay, this generalization becomes meaningful only when you study the case of larger memory size. So I didn't talk about it here because when memory is log n, you can just run the classical collision pairs finding algorithm. It already gives you the best we know how to do. But yeah, it would be, maybe it's possible to improve the upper bound, and in that case, it would be really interesting.
Okay. Any other question? So if not, let's thank the speaker again. Thank you. Okay, so the last speaker of this session is Subhasri Patro from QSoft CWI. Okay, so please start.
Hi, everyone. I'm Subhasri Patro, and I'll be talking about fine-grained complexity via quantum walks. This is a joint work with Harry Bowman, Bruno Loff, and Florian Spellman. Let me begin. Okay. So a lot of money is getting pumped into for quantum computing, like in investing in quantum computing, and rightfully so, because there are a lot of computational problems for which we have quantum algorithms that are faster than the classical ones. And that's because quantum computers are a more powerful model of computation than the classical ones. But what we also notice is that quantum speedup is not guaranteed for all problems. Like, say, for example, for integer factorization or discrete log, we have quantum algorithms that are exponentially faster than the classical ones. But for triangle finding or geometry problems or threesome, the current best known quantum algorithms are just quadratically faster than the classical ones. And unfortunately, for some other problems like longest common subsequence, Fréchet distance, edit distance, we don't even know of quantum algorithms that are better than the classical ones. So a very natural question then becomes as to which kind of problems do quantum computers help? And if they do help, by how much? Like, what is the speed up that we can see? The state of the art is not too bad. Like for problems like unordered search, the speed up that we know is known to be optimal. But again, for TSP or CNF-SAT, like we saw, or some problems that we saw in the earlier slide, the speedups that we know are not known to be optimal. And unfortunately, for problems like recommendation algorithms, we thought we had an exponential quantum speedup, but it turned out that we did not. So again, the natural question, what is the quantum speedup that is possible? And unfortunately, a recent result by Babush et al. Also showed that with the current known error correcting techniques, the quantum speedups that we have, if it is only quadratic, then it is not beneficial for any practical input sizes. So then how do we assert, what if some problem has only quadratic speedup, and how do we assert that? And we can assert that by proving lower bounds. So for example, what we do is we look at these several computational geometry problems where quadratic quantum speedup is possible. And this was a recent result by Ambinis and Larka. Using our techniques, we were able to show that conditional on certain reasonable conjectures, we are able to show that this is the optimum speedup that is possible. And so for people who are interested in solving computational geometry problems, the near-term quantum computers are not going to be beneficial as per the unfortunate result by Babush et al. And the way we prove these results is by using fine-grained complexity. But also, please note that this kind of direction is not new to this paper. Similar quantum fine-grained results have been proven for other problems like closest pair, edit distance, but in recent years. So the reason we resort to fine-grained complexity is because we do not know how to prove unconditional time low bounds. So let me kind of briefly tell about the method that we use. Now, suppose you have this problem A, where people have tried, put a lot of effort in this problem A, they have studied, but they're not able to come up with a fast algorithm for this problem A. And now say we have another problem B, which is interesting, but it is not so much studied as problem A. And we still don't know how easy it is to solve problem B. Now, can we comment on hardness of problem B based on the knowledge about what we know about problem A? We can, if we are able to reduce problem A to problem B. Now, what do I mean by a reduction? So if there is a map that is possible to take an input of problem A and to map it into several inputs of problem B, then using an algorithm for problem B, if we can solve problem A, then we say there is a reduction possible from problem A to problem B. But how is that going to help us? So if there is a fast algorithm to solve problem B, then we could use to solve problem A faster. But we believe that problem A cannot be solved faster, which means there shouldn't be a fast algorithm for problem B. So what we end up doing is we conclude a lower bound for problem B based on a believed lower bound for problem A. So let me summarize again. So we pick a problem A, which is believed to be hard. We reduce problem A to problem B. And then we conclude the lower bound for problem B using this believed lower bound of problem A. And for this paper, what we did, we picked problem A to be 3-sum problem. And we concluded lower bounds for problem like computational geometry problem and zero edge weight triangle finding problem. Now let's look at this 3-sum problem. This is a very simple, easy problem to describe. Suppose we have this list of n integers, and we want to know whether there are 3 elements in that could be repeated, such that they sum up to 0. So in this example, we have the 6 integers, and we do have a solution to this. We have like 3 integers, 1, 4, and -5, which all add up to 0. Now, one trivial way to solve this is to just check all these triples and see if any of these triples add up to 0. But there's a slightly less trivial n-square algorithm, which goes as follows. You take this list, you make a copy of it, you make another copy of it. Now you make a third copy, but you sort it. And now what you do is you take pairs over the first 2 copies and check if some of these pairs exist in the third list with a negative sign. Now, because the third list is sorted, we can check this in log n time. So in about n square log n time, you're able to actually solve this 3-sum problem. Now, for this purpose of the paper, we have ignored any polylogarithmic factors. So, but there is also an n square algorithm for the same problem, which I will not be talking about. But the weird part is people were not able to, substantially improve this n squared algorithm for 3-sum. And eventually it was conjectured that 3-sum requires n square time on a classical computer. And as implications to this conjecture, lower bounds were concluded for a vast collection of computational geometry problems, for sequence problems, for dynamic problems, triangle collection, matching triangles, and zero weight triangle finding problem. But now, what happens in the quantum setting? Can we say 3-sum is as hard as, it's also as hard as the classical, does that also require this much time on a quantum computer? Actually not. We can speed up this same classical algorithm that I talked about and make a n log n quantum algorithm for 3-sum. So you do the same thing. You have this 3 copies. You make a copy and you sort it. You take like n log n time. Now you do this Grover search over all these n square tuples. So instead of and then you do a binary search like just in the classical setting. But because you're grovering over n square tuples, you end up actually only spending n log n time. Now it was conjectured that 3-sum in the quantum setting requires linear amount of time. So because the bounds are different for 3-sum in the quantum and the classical setting, the classical bounds no longer go through. So we picked up this set of problems. We looked at this computational geometry problem. So we looked at the reduction from 3-sum to computational geometry. We looked at the reduction from 3-sum to this zero weight triangle. And we noticed that the way the reduction goes involves a step where first the threesome instance is actually sorted, and then a very local reduction is given. But given that we can't have sorting in under linear time, we saw that these classical reductions are not trivial to port in the quantum setting. And then using this quantum walk type reduction, we were able to reduce threesome to the sorted versions of threesome, and then we were able to give a local reduction from sorted version to these problems. And as a result, we were able to conclude lower bounds for computational geometry problems, a lot of them, which because of this result by Ambinis and Larka, most of them turned out to be tight. And we were also able to conclude tight lower bound for this zero edge weight triangle finding problem. So to summarize, we believe that fine-grained reductions, especially in the quantum case, is a promising way forward to prove lower bounds which are beyond the query lower bounds. And using our proof strategy, we were not just able to comment on the hardness of sorted version of threesome. By sorted, I mean with a promise that the input has to be sorted or ordered in a certain way. We were able to actually give a little more general proof for that. And because of this recent result by Babush et al., we kind of showed that for computational geometry problem, it's not very useful to use quantum computers on near-term devices because the speed up that we can see is only at most quadratic. And the future directions are again many. Like if you notice, we have only kind of closed only some of these, like we have concluded lower bounds, quantum lower bounds only in some of the problem. There are a lot of classical lower bounds that exist, and we would like to explore that. The other thing that we still have to finish is there are some computational geometry problem. Like here, if you see, the upper bounds are still, they're not tight. So either we need to come up with better lower bound techniques, or probably there are faster algorithms that are yet to be found. And thirdly, we feel like there are other key problems, like how we talked about threesome here. There are other key problems also in this fine-grained world where hardness is assumed, and then lower bounds for other problems are concluded on based on the hardness of those problems. So that is yet to be explored in the quantum setting as well. And that seems to be next natural future direction for us. So thank you for the attention.
Okay, thank you very much for your talk. So any question or comment? So I have two questions.
Sure.
So first question is, so here you use threesome, but there are other fine-grained conjectures like orthogonal vectors or all pair shortest path. And so can you obtain similar results if you use other fine-grained conjectures?
Yes. So in fact, the two papers that I cited here, one of them was also by our group, where we gave hardness results for edit distance and longest common subsequence on assuming some hardness on the CNF SAT kind of problem. And the other result was by Aronson et al., where they also assume hardness of CNF SAT in the quantum setting, and they gave tight bounds for closest pair and bichromatic closest pair problem. So, and APSP is also another key problem that you mentioned. I don't know of any quantum results on that, but that seems to be the next target.
Okay, thank you. So the second question is, so your quantum threesome conjecture is you need n time to solve the threesome problem.
Yes.
I guess the motivation of this is in classical case, n squared is the best lower bound for threesome problem. But so is it really the case? So if you use a quantum computer in the first place, even classical threesome conjecture could be wrong. So why you can assume classical conjecture if you use quantum computer?
Oh, that's a very good question. See, the reason why we believe this quantum conjecture for threesome takes only linear time is because the classical one is not able to improve over the unstructured search over these n square pairs. That is the motivation behind the classical blockage that we have. And given that unstructured search doesn't have anything better than quadratic speedup, we also feel that should be the case in the quantum setting as well. But the conjectures that we give are not, like, basically the quantum conjecture is not implied by the classical, or the classical is not implied by the quantum. It is, we get the intuition and we hence think of the hardness that way, but they're not mathematically related.
Okay, thank you. So, any other question? Okay, if not, let's thank the speaker again. Thank you. So this is the end of the session. So we have break now.
Hello there.
Hello.
Shima, right?
Yes.
So, actually, I'm not 100% sure how this session could proceed. So you will give it will give you 10 minutes to answer the questions, or you need a few minutes to introduce your talk.
No, I'm going to give a talk for 5-6 minutes, and then it will be for the questions, like 4 or 5 minutes for questions.
Okay. Okay. All right. So we are about time. All right. So welcome to this session. Good day to everyone. It's afternoon here, so I assume that some of you are in the morning, some of you in the night. The first talk will be given by Shima Hadasha, so who will give us a talk about the one-shot quantum state redistribution and quantum Markov chains.
Yeah, so do you see my slides?
Yes, I can.
And you can hear me?
Yes.
Okay, great. Yeah, so hello everyone. Thanks for the introduction. I would like to also thank all the organizers for providing this opportunity. So I'm going to talk about one-shot quantum state redistribution and quantum Markov chains. This is based on a joint work with Anurag Anshu, Rahul Jain, Ashwin Nayak, and Dave Touche. So as you may know, quantum state redistribution holds an important place in the theory of quantum communication. And in fact, it can be considered as the most general version of quantum data compression. So in this task, there is a four-partite pure state row RABC, such that registers A and C are with Alice, register B is with Bob, and register R is with referee. And Alice wants to transfer register C to Bob coherently using a noiseless quantum channel and some shared entangled state. This task is well understood in the asymptotic and IID setting and has communication rate given by the conditional mutual information of R and C given B in the state row. Also in the one-shot setting, there have been many efforts to characterize the optimal cost. However, all known bounds are suboptimal, especially for the set of quantum Markov states. For example, if the register R is trivial, meaning that the register row is pure over registers A, B, and C, then the cost of all previously known protocols can be as large as log of dimension, whereas the optimal cost is obviously 0 because Alice and Bob can just initially share the entangled state, share the desired state as their entanglement. So in this work, we introduce a new one-shot protocol with a smaller cost that is optimal for the previously special case as well as quantum Markov states. And a motivation for our bound is coming from the fact that quantum conditional mutual information can be written as the difference between relative entropy of rho RBC and sigma RBC and relative entropy of rho BC and sigma BC when we are minimizing over states sigma RBC that are quantum Markov states and also extensions of rho RB. And so the cost of our protocol is a one-shot analog of this characterization of conditional mutual information, where the relative entropy is replaced by smooth max relative entropy in the first term and by hypothesis testing relative entropy in the second term. As far as we know, this is the first result that connects one-shot quantum state redistribution and quantum Markov chains, and it gives an operational interpretation for a possible one-shot analog of quantum conditional mutual information. Also, if a rho RBC is classical, then here we can choose sigma BC equal to rho BC, and so our bound reduces to a one-shot version of classical conditional mutual information. And finally, the cost of our protocol is tighter than all previously known bonds. In particular, the best previously known bond is a similar bond due to Anshu, Jain, and Warsi, where the minimization is over only the set of product states between systems R, B, and C, rather than the set of quantum Markov states. So let me briefly explain the high-level idea behind our protocol by explaining a folklore zero-cost protocol for redistributing quantum Markov states. So as a result of a work by Hayden, Joseph, and Winter in 2004, it is known that if rho RBC is a quantum Markov state, then its purification, rho RABC, can be transformed to a state of this form through local isometries VA and VB, such that here registers AR, J prime, AC, and C are with Alice, and registers BR, J, and BC are with Bob. And conditioned on registers J and J prime, registers R, BR, and AR are decoupled from registers AC, BC, and C. So in order to redistribute register C, Alice and Bob first condition on registers J and J prime, they embezzle out systems AC, C, and BC, and then they embezzle in the same system such that now registers BC and C are with Bob and register AC is with Alice. So this protocol only works for redistributing quantum Markov states, but our protocol is a more sophisticated version of this protocol. And in order to make it work for any arbitrary state, we use the coherent flattening via embezzlement technique due to Anshu and Jain, and also the convex split and position-based decoding techniques that have been used in the AJW protocol. And if you're interested to know more about our results, I really encourage you to watch our pre-recorded talk on YouTube or visit our submission on archive. And with this, I would like to conclude my presentation. Thank you for attention, and I would be happy to answer any questions.
Great, thank you very much. Any questions? Okay, I have a quick one.
Sure.
So that's a very nice work.
Thank you.
Do you have any applications on, let's say, cryptography or computing for this work?
You mean for the quantum state redistribution?
Yes.
I mean, one application, one very important application is in a communication complexity setting. So there is a very important open problem called direct sum problem. And in order to prove this direct sum problem for a bounded round setting, when we have two parties who can communicate with each other, and there is a bound on the number of rounds of communication, this protocol can be used to prove quantum state redistribution can be used to prove direct sum if we can show that the communication cost is bounded by conditional mutual information in the one-shot setting. So if we can show this, then it will prove direct sum theorem for quantum bounded round communication complexity.
Okay, all right, thanks.
Yeah.
Any more questions? Let me check out the question. Okay, if not, let's thank the speaker again and move on to the next one.
Yeah, thank you very much.
Thank you. The next talk will be given by Zahara Bagali, who will give Kania, who will give us talk on the quantum state redistribution for ensemble sources. Zahara, whenever you are ready.
So shall I share my screen now?
Not yet, not yet. I cannot see your screen.
Do you see my screen now?
Yes, yes. All right, thanks. Please continue.
Okay, hello everybody. I'm going to talk about quantum state redistribution for ensemble sources, which is a joint work with Andreas Winter from Autonomous University of Barcelona. So in order just to give a very short background, as you might already know, quantum state redistribution is a source compression problem where both the encoder and the decoder and encoder have side information. So this problem was for the first time studied by Devetok and Yard in 2009. So they consider a pure state shared between an encoder who has access to registers A and C. And this encoder wants to compress system A and send it to a decoder which has access to side information B. And also all of these source is correlated with a reference system R. And basically this protocol is known as quantum state redistribution. And it has been shown that the optimal quantum compression rate is equal to the half of the mutual information, conditional mutual information between register A and R given B. So in this work, we consider the most general setting of quantum state redistribution, that is an ensemble source. So as I introduced previously, quantum state redistribution studies a purified source, but here we consider an ensemble of states coming from an ensemble with some probability distribution. Similar to quantum state redistribution, we have register A and C, which are in the disposal of the encoder, and the system A is the system that we want to compress and send it to the decoder who has access to side information B. And system R is the purifying reference system as well as the reference system X, which plays the role of the classical variable of the ensemble. So we consider many copies of the source similar to Schumacher and also quantum state redistribution compression. So here I have denoted the task. So as I already mentioned, we have an encoder and decoder, which we generally can consider them as CPTP maps. So we have many copies of the state. System A is the system that we would like to compress and send it to Bob, the decoder, via a noiseless quantum channel. And Bob wants to decode this information, A, and also its his side information, B, in such a way that the overall correlations with the reference systems R and X are preserved. We also consider that Alice and Bob, the encoder and the decoder, share free entanglement in registers A0 and B0. Okay, as for the figure of merit and how we want to decode this information as indicated here in this picture, we consider two figures of merit. The first one is block fidelity, that we want to keep the fidelity for whole blocks of n states. And the other one, the other criteria that we consider is per copy fidelity, which instead of considering the keeping the blocks of states intact, we want to just preserve the fidelity for each copy of the state in average. Okay, so since we consider two figures of merit, considering each figure of merit, we define the optimal compression rate. For example, considering block fidelity, we call the minimal achievable rate QB, and also considering per copy fidelity, we call the minimal achievable rate QC. Okay, in order to make connections with the conventional quantum state redistribution, let's just recall the rate of quantum state redistribution, which was half of the mutual information between the sender, system A, that we wanted to compress, system R, which is a reference, given the side information at the decoder side. So our optimal compression rate is going to be in terms of a single letter function which is a function of this source that I already introduced. This is our single letter ensemble source, and consider its purification, where this register X prime purifies this source here. Sorry. So we defined a Q of epsilon function as the infimum of over this kind of mutual information, which resembles a lot to this quantum state redistribution, that conventional quantum state redistribution. However, we have an optimization here over one copy encoder and decoders. So this might seem a bit complicated, but if I want to expand on this function, it's just optimization over this single letter encoder and decoder. So our encoder just maps a system A and the side information system C to the compressed information Z and the reconstructed side information, and also our decoder gets the compressed information and together with the side information of himself B. He aims to recover system A hat and B hat in such a way that the fidelity is preserved. So this is the function and the quantity that plays the most important role in our results. So the first one that I would like to say is the limit of this function. We denote it by Q tilde of 0. And the other important quantity here is the value of the function, which we denoted by Q of 0. So unfortunately, this function has some properties that we don't know very well. For example, we don't know if this function is continuous at 0 or not. So there are some problems. For example, there's not a priori bonds on system Z, so we cannot use the conventional discussions to show that this function is continuous at 0 or not. And the main result of this paper is that we show that considering per copy fidelity, the optimal compression rate is equal to the limit of the function at 0, and considering block fidelity, we find upper bound and lower bounds on the optimal rate. So the upper bound is the value of the function at 0, and the lower one is the limit of the function at 0. And if we were able to show that this function is continuous at 0, we basically can show that whether we consider block fidelity or per copy fidelity, it doesn't matter. We get the same optimal compression rate. However, we don't know whether that is true or not. So with that, I would like to conclude my talk.
Thank you very much for a nice talk. Any questions? Okay, let me check the Q&A. Okay. Questions. Okay, no. All right, so if there's no questions, I would like to thank Zara again for a nice talk. And the next talk will be given by, hang on a second, let me check. Okay, let me check it. All right, so next talk will be given by Alexander Marcin Kubicki, who will give us talk on. Sorry for the bad pronunciation. Who will give us talk on the entanglement consumption in a text to position-based cryptography from geometry of Banach space.
Thank you very much for an introduction. Thank you all for attending this live session in which we will be discussing our latest work on position-based cryptography. So let me share my screen. Okay, I hope that you can see the presentation now.
Yes, we can.
Yeah, thanks. So in this work, we propose the study of this cryptographic setting using tools from Banach space theory. So in particular, sorry for that. So in particular in this work, what we have studied is a protocol for position verification in which a pair of verifiers try to verify the position of a prover in the middle of them. And for that, they communicate to the prover quantum classical messages and require the prover to implement some quantum operation, which is determined by this classical message epsilon coming from one of the verifiers. The ideal output is that the prover send back to the verifiers the outcome of the computation. In this scenario, we want to analyze the resources that a team of cheaters need to use in order to break the security of the protocol. To do that, in this work, we have made two important simplifications, which are the following ones. So first, we just disregarded classical resources, considering them just as free. The second simplification is that we didn't make any attempt to take into account computational complexity considerations here. With all that, what we study is the dimension of the Hilbert space of the quantum systems that the cheaters manipulate in their attack. The existence of generic attacks for position verification translates into this setting as upper bounds for this quantity, which is the main quantity of interest for us. And these upper bounds are exponential in some power of our parameter n, which determines the dimension of the quantum systems that are manipulated in the honest implementation of the protocol. The main goal of our work is make some progress in the understanding of lower bounds for this quantity here. The main results that we obtain are this kind of lower bounds, which are exponential in this parameter n for some constant alpha, but the lower bounds that we were able to prove relies on the validity of some additional assumptions that we have to make. So in first place, we prove this kind of bounds for strategies of the cheaters that depend on the classical index epsilon in a way which is regular enough. And this is specified further in the paper that you can check in the archive. In our second result that I presented here, we drop out this regularity assumption and look for the landscape for general attacks in this setting. And we prove similar lower bounds, but now taking into consideration a conjecture that we make on the geometry of the Banach spaces that appears in our analysis. In our work, we provide some evidence supporting this conjecture, but so far the validity of the conjecture is still an open problem for us. The main idea behind the proof of these main results is understanding the action of the adversaries for our protocol as functions, as Boolean functions, taking values on some well-suited Banach space X. Constructing these functions in a proper way, we are able to relate the study of the function with the success probability that the cheaters attain in their attack. Therefore, we translate the study of our position verification setup into the study of these kind of functions here. And for that, the main technical tools that we use are, in first place, kind of Sobolev inequality discovered by Pizier, and the theory of type and cotype of Banach spaces. Using these tools, we can obtain this kind of generic upper bounds for this quantity, and controlling the right-hand side of the inequalities, how we can get the claimed results. To conclude this short presentation, I will say just a few words about some interesting future directions that are opened in this work. So the first one is the possibility of generalizing our ideas and the techniques that we introduce in this problem to the study of other protocols. So in particular, it would be especially interesting to try and understand protocols in which the messages that the verifiers prepare are just of lower dimension, much lower dimension than in our work. Okay, an important feature in part of our result is this regularity assumption on the attacks of the cheaters. And so far, the understanding that we have about this kind of regularity assumptions or regularity parameters that we consider for the attacks in this protocol. Our understanding of these parameters is not is quite poor yet. So it will be very interesting to deepen on this question. So we also related the problem of studying position-based cryptography and attacks to position-based cryptography with some open questions in Banach space theory. And finally, it's also interesting to notice that recently appeared some connection on the study of position-based cryptography with duality in the context of ADS-CFT. So it would be also interesting to try and understand whether the techniques that we use here might have some application there. And with that, I conclude my short presentation. I look forward for your questions in case there is any. Thank you.
Thank you very much for the nice talk. Any questions? I have a question related to the second open question you pointed out. So do you expect, like in general, let's say, because in this talk you are talking about a very specific attack, at least a specific set of attacks. So if we talk about general attacks, do you expect some exponential complexity from the hacking point of view?
Well, so the initial motivation to consider this kind of regularity assumptions on the attacks is that known attacks for position-based cryptography, or at least some of them, in fact, fulfill these conditions. So are in this sense are continuous enough or regular enough. But in general, we don't have any clear clue about whether breaking this kind of regularity, you can use much less resources in order to cheat this kind of cryptographic setting. But, well, my expectation would be that this might be somehow a general feature of, or at least this regularity assumptions, these regularity properties might be related with some desirable properties from the physical point of view of the protocols that the cheaters apply. But we don't know so much about it. Thank you.
Okay. All right. Thanks. All right. Any more questions? Okay. If not, let's thank the speaker again and then move on to the next talk. Hang on a second. Okay. Next talk will be given. Hang on a second. I think the next talk is given by Felix, right? It is. Okay, Felix, are you around?
Actually,
oh, you will give talk?
Felix couldn't make it, and I will represent him and other coders.
All right, so next talk will be given by Carol Horodoki, who will give us talk on the upper bounds on device-independent quantum key distribution rates.
Yeah, let me share the screen. Do you see my screen? Okay.
Yes, we can.
Okay, sorry. I'll just make it first slide. I'm sorry for that. Okay, here we are. Okay, so thank you for this nice meeting. Yeah, like I said, on behalf of authors, so on behalf of Rotem Arnon Friedman and Felix Leditsky, I would tell about their results related to upper bounds on device-independent quantum key distribution rates and revised Perez conjecture. And on behalf of Matthias Christian, Roberto Ferrara, and myself, I will tell about upper bounds on the rate in device-independent quantum key distribution. So just to begin with, what is the device-dependent scenario in quantum cryptography? This is the one when two parties share bipartite quantum state, eavesdropper shares purification of it, and the parties trust both the dimension of the quantum state and the measurements mxa and myb that can be performed on them during protocol of key distillation. And here relevant quantity is KDDs, device-dependent key. While in device-independent scenario, the parties share an unknown quantum state and they don't know dimension of it. And also they don't know which measurements actually devices perform. So the measurements are performed in the closed devices, they cannot open them. And they trust only the statistics of inputs X and Y and outputs A and B. So here the relevant quantity is device-independent key, which is KDI. And because in the device-independent scenario, if has much more ways to attack, then it is trivial to observe that KDI cannot be larger than KDD. So KDI is less than or equal than KDD. And the goal is to go beyond this trivial inequality and prove some interesting non-trivial upper bounds on device-independent key. So in the first part, I will tell you about the results of Roteman, Friedman, and Felix Levitsky. They have placed an upper bound, which is based on intrinsic information and also on attacks on devices that works for standard protocols. And by standard protocols, they mean the protocols that in which the key is achieved by a fixed pair of inputs X hat, Y hat from a device which is represented by a conditional probability distribution PAB given XY. And specifically, they also consider a situation in which only the key is only a function actually of two parameters, the Bell violation, level of Bell inequality violation, and the error in correlations when measuring X hat, Y hat. And the device-independent key in this case is upper bounded by a function which is intrinsic information, which means it's conditional mutual information minimize actually over channels of Eve acting on her share. And what is more important, which is minimize, which is this infimum here, minimize over states small sigma here that are compatible, that belong to set large sigma. A big sigma is they are compatible with the statistics that I mentioned, which are the level of the Bell inequality violation and the error rate in correlations. So this is actually a novel, quite powerful upper bound. This is the main result. And the second main is that they consider a state which stays positive under partial transposition that is known to exhibit non-locality. And they show that this state actually has zero one-way device-independent key. So neither from Alice to Bob nor vice versa, one can distill key by a standard protocol. So the protocol that bases on the Bell inequality involved in this non-locality, exhibiting non-locality of this state. And from that, they conclude as they put forward a conjecture that all PPT states with positive having positive partial transposition do not have positive quantum DIQKT key rate, right? So this is an open problem now. And in the second part, I would like to tell you about results obtained in collaboration with Matthias Christan and Roberto Ferrara. So we provide an upper bound exhibiting a gap. Here we consider a device-independent key as a function of a state. So we consider devices achieved by measurements M on state rho, and then we take supreme over these measurements. So this quantity is now a function of a state solidly, and we call it device-independent key of a state. And actually, we proved that it can be much, much smaller than device-dependent key of a state. So the KDI can be close to 0 and KDD can be close to 1, for example. So we give examples of low-dimensional states with the gap, the above gap. And the lowest dimension that we give example is the 6 qubit by 6 qubit bipartite state. And we also provided a sufficient condition for the gap to hold. And these states has positive transposition, so this kind of supports the conjecture at least it shows that these states can have low device independent key. Maybe non-zero, we cannot prove zero in this case, but low amount of device independent key. And then we extend the results to the scenario of quantum channels, where we explicitly consider the attack on the quantum channel. So the eavesdropper not only affects the measurements, not only affects the states, but also a quantum channel that is explicitly taken into account. And then we prove that in the case of channels that are positive under partial transposition, PPT channels, some of them have smaller private device-independent private capacity than the usual private capacity. And with that, I would like to thank you for your attention, and I'm happy to answer questions if there are any.
Thanks a lot for a very nice talk. Actually, there's some problem with my computer. I couldn't. I don't know if you can hear me, Carol.
Yeah, I can hear you.
Oh, okay. Okay. Any questions? Any questions? Hang on a second. There's something wrong. So I remember that a long time ago, there's a paper by photography plus Huai-Kong. So there's a very nice paper saying that we can distill the key positive key from the positive key rate from the a bounded integral state. So in that case, if that bounded integral state, if that's the fall into the category of the PPT state.
Yeah, sure. They are. I mean, the only known bounded integral states that we know are these that have positive partial transposition. Yes, and this is the issue here, that they can have positive key, a device dependent key, but yes, the device independent. Some of them device independent can have very low. Yeah.
Okay. I see. All right. All right. Thanks for the nice talk. Any more questions?
Yeah.
Okay. If not, let's thank the speaker again, and let's move on to the next talk. All right. Next talk will be given by Jiahui Liu, who will give us a talk on the new approaches for quantum copy protection.
I think the previous speaker has to end the screen sharing before I can do my screen sharing. Okay, thank you.
Actually, I cannot see that because my computer is frozen at some point.
Okay, so
I can hear you, but I'm not sure if your slides are shown.
I believe it is shown.
Okay. Yeah, let's go ahead.
Okay. Yeah, like just in case if the audience, like anyone in the panelists who can, if you guys can't see me, just let me know. Okay, I'm going to talk about new approaches for quantum copy protection. As we know, quantum no cloning principle does not allow us to copy an arbitrary quantum state. So quantum states cannot be copied in general, and this has been applied a lot in quantum cryptography. One famous example is quantum money put forward by Wisner many years ago. A quantum money state encodes a money value and serial number. A valid money state can get verified by the bank, but the user with one copy of money state cannot produce two copies that can both get past the verification. And we wonder if we can leverage such a scheme to encode more complicated classical information into unclonable quantum information. Then we can take advantage of. For example, Ericsson in 2009 put forward quantum copy protection. A copy protection algorithm turns a classical functionality, F, into a quantum state. This state can be used to run on any input such that you get the same evaluation as the original function. But a polynomial bounded adversary cannot turn this state into two states that both compute the functionality f correctly. Erson also gave the first construction for any unlearnable functions using a quantum oracle. So what's an unlearnable function? An unlearnable family of functions is a family of functions that cannot be learned through its input-output behavior by a polynomial time adversary. It's clear that here, when we say unlearnable, we also mean quantum unlearnable, because the adversary who's querying the oracle is a quantum one. It's clear that if a function is learnable, it can never be copy protected, because the adversary can just recover the functionality from the program by learning it. But one drawback of Erson's scheme is that he has to use this quantum oracle. Quantum oracles are oracles that implement functionalities of quantum circuits. And classical oracles, of course, implement only classical circuits functionalities. Now, both kinds of oracles can be heuristically implemented by a cryptography assumption called virtual black box, in short, VBB obfuscation, which scrambles a circuit and make it no different from accessing an oracle. Both of these assumptions, the quantum version and the classical version, they are somewhat wild. But the obfuscation for quantum circuits is still a stronger assumption than the classical one, and it's one that we understand less. Therefore, Erson in 2009 also asked if we can build copy protection using only a classical oracle. And we answered this question with a yes in our results. Our main results can be divided into three parts. First, we briefly go through some improvement on definitions. As we mentioned before, the adversary in the copy protection has to produce two Pyro programs, then compute the functionality correctly. How do we test if a Pyro program computes correctly? We may run into issues like the Pyro programs, they cannot be gentle measured. They cannot be run for multiple times. They may destroy after one run, and they may be entangled. Because the adversary produces two programs, they might be entangled in some sense, and they may be partially correct, but despite these issues, they may be still meaningful Pyro programs, so that some freeloading users can use them. And we need to find out about these programs. So in our paper, we give a way to test Pyro programs efficiently when facing these problems. Next, we give our construction to copy protect unlearnable functions relative to a classical oracle. We're inspired by the hidden subspace idea from Erson Cristiano's quantum money scheme in 2012. A hidden subspace A is a secret subspace randomly chosen by the challenger. It has exponentially many elements, but still it's exponentially small compared to the full space, which is, for example, an n-dimensional vector space over finite field of 2. A subspace state here, cat A, is an equal superposition of all elements in A. Subspace states has the following properties. If we do QFT to a state, we get its dual subspace state with the vectors in A perp, and we measure it, we get a vector in A perp. And moreover, it has the following important property. Consider the problem. If we give a quantum adversary with one copy of A and access to membership oracles for A and A perp, which check if an input vector is in A and the input vector is in A perp respectively, and given all this, a quantum adversary bounded polynomially in queries cannot output two vectors, one in A and one in A perp. And this is a provably hard problem, and our security will rely on it. And our copy protection construction basically is as follows. It consists of one copy of the state, the subspace state A, and two oracles. And each oracle, it checks if a part of the input is in the subspace A and A perp, respectively. And then they give a secret share of a function evaluated on X, combining these two outputs from these two oracles. A user can recover the correct evaluation of F. And for security proof. We won't go into details here, of course. If basically, if a quantum polynomial time adversary is able to produce two programs that both compute F correctly, it will violate the hard problem, as we mentioned just now, or violate the unlearnability of F. And the next step we will think about, can we implement our oracle? Can we move to a construction using more practical cryptography assumptions? However, unfortunately, we have a barrier if we want to remove oracles. A concurrent work shows that using a post-quantum cryptography assumption called learning with errors, a believably called a post-quantum one, and quantum fully homomorphic encryption with certain properties, we can build a circuit that is unlearnable, but it can never be copy protected. So we can hardly achieve a general copy protection scheme without oracles that we can say we can protect all unlearnable functions, unless we want to go against these two well-founded assumptions. In the face of this barrier, the next achievable directions are: the first one, consider weakening security notions. Are there weaker but meaningful security notions for quantum copy protection that we can do better? And the second direction is, we don't relax the security requirement, but we consider smaller classes of functions to copy protect. For example, we just give a specific construction for point function or for PRFs, and we will focus on the first direction here. We put forward a notion called copy detection. Instead of allowing the adversaries to win with any Pyro programs that compute F correctly, they also need to pass an additional test that tries to check if the programs are Pyro programs instead of authentic ones. So the adversary not only needs to produce programs that compute F, but they have to have certain features so that they won't be found out as Pyros. Using this notion, we can achieve much larger classes of copy detection. We achieve copy detection, actually publicly detectable copy detection for any watermarkable functionalities. And security relies on watermarking and combined with public key quantum money. Watermarking, for those who are not familiar, it's a classical cryptography tool that allows you to embed the watermark into the circuits so that no adversary can remove this watermark while not damaging the function. So watermarkable functions include a lot of cryptography functions, such as pseudo-random functions, public key encryption, and signatures. Thank you. That's everything in my short talk, and please refer to our paper for more details. I'm happy to answer questions.
Well, thank you very much for a very nice talk. Any questions? Any questions? That's a really very nice talk, and it's good that we have something we can protect the copyright. Unfortunately, there's something wrong with my computer. I cannot see all the slides that we didn't talk. Any questions from the audience? Okay, if not, let's thank the speaker and all the speakers in the session. Oh, there's a Q&A session, actually. Yeah, okay. Hang on, let me check it. Q&A. Screen. Yeah, somehow I can't see the question. Is it possible that someone can read out the question for me, please? Oh, it's here. It's here. Oh, it's already answered. Yeah, shoot. Actually, it's about question how to put in the questions. It's not the question for you. All right, thanks a lot for the talk, and yeah. If we have any further questions, we still have the videos online on the YouTube. We can check it out, and also we can email the authors directly. Okay. All right, so maybe we can just conclude here. All right. Thanks a lot. All right, let's take a break.
Okay. Hello, ladies and gentlemen. Welcome to the first afternoon evening session, the second day of TQC. This is Hao Cheng from the National Taiwan University. We are very happy to have 5 talks in this session. The first speaker is Leonardo from University of Florence. He will talk about generalization in quantum machine learning, a quantum information perspective. Please go ahead, Leonardo.
Thank you. Let me share the screen. Okay, so I guess you can all see my screen. If not, let me know. So my talk is based on the following paper here at the bottom, which is a collaboration with Jason Pereira and Stefano Pirandola, and you can find it on the link shown in the archive. Okay, so let me define the problem studied in our paper and consequently in this talk. So we want to classify states rho of X that depend on some external classical parameters X, and this can be tuned. Now, this problem differs from the perhaps more standard problems of quantum state and channel discrimination or even quantum hypothesis testing for 2 reasons, I think. So the first one is that we don't have to learn X, but rather the class of the states, this rho of X. And even here, this can be done using a P of M, whose outcome is the predicted class. And the second difference is that we don't know the data distribution, so we don't know the P of X. So what we do know is a collection of T correctly classified states, which are pairs rho XT and the corresponding class CT, which form what we call a training set. So for instance, in this picture on the top right, so we have 2 classes, class 1 and class 2, and the states rho x1, rho x6, and so forth belong to the first class, while the others, rho 2, and so forth, belong to the second class. Now, we can build a classifier, for instance, by optimizing the P of M using the available information that we have. Namely the pairs in the training set. But what happens when we have a new state? So something that was not present in the training set. So we can empirically check whether the classifier generalizes, namely is able to classify even unseen data using what is called a testing set. But on a more theoretical ground, so given a problem, so what kind of training and testing errors should we expect? So this is the main question of my talk. Okay, I want to clarify that several problems can be described using the formalism that I've just mentioned. So for instance, we may be interested in classifying whether the states produced by some quantum device are entangled or not. And here, for instance, X are some tunable experimental parameters that one can vary. Or we may want to classify the phases of a quantum many-body system. And in this case, the parameters X are, for instance, the external magnetic fields. Or other applications are in quantum sensing or illumination or quantum reading, where the parameters X model the objects living in the physical world. And for instance, in this car at the bottom here, this car is enhanced, let's say, with some quantum light. And the task here is to decide whether to stop or not the car, depending on the state rho of X, which is received by the detector. And finally, we may also focus on classical machine learning with quantum classifiers. So for instance, we may want to classify classical images to check if there is a cat or not in these images. And we do this by first embedding the image, so the classical data, into a quantum state via a parametric quantum circuit, like the one shown here and on the left, and then performing a measurement. Now, in all of these examples, we assume that we were able to perfectly characterize what happens for some particular values of X. And so the question is that to see also what predictions we can make about new values of X, so not present in the training set. Now, in this slide, I now summarize what are the main results of our theoretical analysis. So we have shown that the generalization error, which is roughly speaking the difference between the average testing error and the average training error, is bounded by this B quantity divided by the number of samples. And I will describe this B quantity later. So if you increase the number of training samples, the generalization bound decreases as we expect. So the generalization bound can be shown also in this, is shown also in this picture here on the top left as a cartoon, where the average testing error is the blue curve and the average training error is the red curve. So we may also introduce another error, which is the approximation error. And the approximation error, on the other hand, describes the difference between the optimal quantum classifier and the theoretical optimal classifier, which is somehow given by the bias rule. So it's the bias classifier. Though, so we don't know any of these two, so neither the theoretical optimal quantum classifier nor the bias classifier, because we don't know the data distribution. So we just have some training samples. So here, indeed, the only thing, so we assume that the only thing we can do is to do some measurements on a quantum device. So our ability to classify the inputs will depend on what is called here the quantum embedding. So namely the mapping from the classical parameters X to the quantum state rho of X. So this cartoon picture on the top right shows qualitatively the an intuition that we get from statistics. Namely that one can expect that the training error decreases by increasing the model complexity, but the same is not true for the testing error. Namely, for too many parameters, the model typically overfit the data. Now, both quantities entering in the generalization and approximation errors can be expressed using entropies. And the expression of the generalization bound using this B quantity is the main technical result of this paper. So the B quantity in the generalization bound depends on the Renyi true mutual information between the quantum embedding and the classical input space, while the approximation error depends on the mutual information between the quantum embedding and the class space. And the entropies that enter into the generalization and approximation errors are defined for this state at the bottom, where Q refers to the quantum embedding and C and X are respectively the classical class and input spaces. Okay, so our results define a computable bounds on the approximation and generalization errors. So based on those bounds, we can prove a quantum version of the bias variance trade-off, which is a fundamental result in statistics that states that it's impossible to minimize the approximation and generalization errors. So this area here on the red is not achievable. Then using data processing inequality and other tools, we can also show that, for instance, if we increase the Hilbert space dimension, then typically generalization error increases while the approximation error decreases. And the opposite happens with noise. Because noise makes all the states look more similar and less dependent on the inputs. So what happens is that the generalization decreases, but the approximation increases. And also what we call here pooling layers are, let's say, quantum operations that iteratively discard information by reducing the Hilbert space dimension. So intuitively, what a classifier should do is somehow to discard as much information about the input, which is not necessary to predict the output, which is the class. So if this is done by a quantum operations, then we show that this is the trend, namely approximation error increases, generalization error decreases, while the approximation error increases. So based on this intuition in the paper, we also define a quantum version of the information bottleneck principle that allows one somehow to tune the amount of discarded information. So let me jump to the conclusions. So we have introduced a framework to bound the training and testing errors via information theoretic quantities, namely mutual informations between classical and quantum variables. So we can use our bounds to formally prove different observations that were numerically observed in the literature. And the proof is typically quite simple, using standard tools such as data processing inequality. And finally, we have also introduced a quantum version of the quantum bias variance trade-off and of the information bottleneck principle. So with this, I thank you for your attention.
Okay, thank you, Leonardo, for a great talk. We are open for questions. I actually have one question. So how to train the embedding CQ map in your model?
Sorry, how to constrain?
How to train your embedding map, the CQ map from X to row X.
So in our paper, we focused mostly on fixed embedding. So we fixed the embedding. So we focus mostly, let's say, on these applications here. Not necessarily on the classical data. So we have a quantum embedding fixed, and what we train is the POVM. So okay. the POVM, but. So one can also, as you mentioned, also train the embedding if one wants to. And for instance, one can train also this approximation error here. But what I think is the most interesting, in my view, way of training the embedding is to use the information bottleneck principle that I didn't have time to discuss here because of I mean, lack of time, but is discussed in the extended version of the talk and in the paper.
Okay, I see. I think it's about time. Let me thank you, Leonardo, again.
Thank you.
Yeah. Okay, so let's move on to the second talk. The second speaker is Christopher Trapp from the ETH Zurich. He will talk about tensor network decoding of arbitrary 2D polycodes. Please go ahead, Chris. Hi, yes, I can hear you.
Okay, cool. So, okay, this is visible, I'm going to assume. Right, so thank you to the organizers for this opportunity. So as was said, I'm going to be talking about tensor network decoding of arbitrary 2D polycodes today. So one of the nice things about polycodes, especially under Pauli noise, is that the optimal decoding procedure can be succinctly described. And it's given by something called the maximum likelihood condition. This is referred to as the maximum likelihood decoder. So here, all you have to do is you take the syndrome data, you calculate the associated error classes, and then you just have to maximize the, you have to find the error class with the highest probability in your error model. So this gives you a really succinct description of optimal decoding for these codes, but obviously there has to be a catch. Otherwise, you know, it can't be that easy. And the catch is that these error class probabilities are exponentially large sums, right? So for a stabilizer code, for example, this involves a sum over the entire stabilizer group, right? So this is the thing that makes this this expression not so easy to do in practice. The technique that we look at in this paper to sort of practically attack this is to say, well, you know, these class probabilities involve exponentially large sums that are potentially difficult to evaluate. That's also true of tensor networks. Can we connect the two and then, you know, leverage tensor network techniques and sort of pull them back to give you a decoding scheme? So there's, you know, been work for quite a while, sort of looking at the connection between quantum error correction and tensor networks. There's even some previous, there's some previous work looking at this explicitly to do tensor network decoding. But these constructions were very code specific, right? So this work, for example, looked at the toric code specifically. So in some previous work with my PhD supervisor, Steve Lemire, we actually looked at, this is sort of a side effect, we were actually looking at the connection between these class probabilities and statistical mechanical models. But a side effect is that it also lets you give a general construction to take you from these class probabilities to tensor networks, which is pretty handy. So that's the work that we sort of built upon. And this works for an arbitrary Pauli code. So this lets us reduce the problem of optimally decoding a 2D code to the problem of contracting a 2D tensor network. So how do we go about that? So all the previous work was built on this algorithm by Verstraete and Serac, which I'm just going to briefly outline. So here the idea is you start with some tensor network that's in, say, a 2D grid. You start by considering the leftmost column. You then will absorb in the next column by doing a tensor contraction. This now causes these bonds to grow. And if we didn't do anything, this would cause an exponential growth in these bonds eventually and give an exponential time algorithm. But here we can use a tensor network technique known as bond truncation, which lets us essentially compress this back down. You can think of it like a lossy compression. So this is a heuristic. And then, you rinse and repeat, right? You keep doing this until eventually you're just left with a single column. And then these are just matrices you can multiply together until you have an answer, okay? So as I said, all the previous work is built on this algorithm. So what's the problem? So the key problem is that this method is built on this idea of columns. And so this limits the applications of it. So the first issue is, what if I have an irregular network? What does a column mean in this case, right? You maybe come up with a definition, but it's not straightforward exactly how you would define columns in this setting. The other more subtle one is, how do we find these columns algorithmically, right? So in previous work, looking at decoding on, things like this rhombile lattice, this is from a previous paper, the way that it was dealt with there was you sort of massaged it into the square grid, but this was, done by hand, right? You had to sort out this network. It wasn't done, algorithmically, right? I propose in this paper a sweep line contraction algorithm, which sort of extends this Verstraete and Serac algorithm, but alleviates both of these by removing this notion of columns from it. So obviously, with time constraints, I don't have time to go over the full details of the algorithm, but I have a little animation here on sort of the rough idea. So here we sort of are going to sweep along the network as we go, contracting in tensors into this 1D tensor network here on the left. So the key thing is we have no notion of columns here. This is perfectly well defined for random networks, and it's completely algorithmic. I didn't need to massage the network at all as I was beforehand, right? You just put in a random network and it'll run. This is the idea, at least. Okay, so this is a nice proposal. Does it work? So to check that it worked, I looked at a bunch of codes that we ran into this to test it. Most of the codes that we looked at were based on the surface code, which is a generalization of the toric code. The nice thing about the surface codes is they're very flexible. You can put them on any planar graph. These are codes defined by having these sort of planar, these plaquette and vertex type generators, much like the surface code. So we looked at a whole series of surface codes on regular graphs, such as triangular, hexagonal. We also looked at a bunch on irregular graphs, so random triangulation, random tetravalent, random trivalent, things like this, which is something that a lot of previous decoders can't really deal with. For completeness, we also looked at a few non-surface codes in 2D. So we looked at the color code and something called the subsystem surface code, which is a non-abelian version of the surface code. So here's a sort of summary of our results. Again, obviously I don't have time to fully go into details, but the long and the short of it is in all of these situations, we got very, very close to optimal, which is quite nice. So, here are the classes of codes that we ran it on. We ran it for bit flip, phase flip, and depolarizing noise, just as sort of tests. And in all of these situations that had previously been run, to my knowledge, this gives sort of state of the art, some of the best thresholds known. And we're able to run for a bunch of codes that previous decoders could not run on and give seemingly optimal thresholds, which is quite nice. Okay, so I think this leads in my conclusion here. So we showed a technique that gives you, highly flexible and effective 2D decoding in general, which is quite nice. There's a bunch of obvious future directions, measurement errors, 3D, things like that. These are my links if you want to contact me. And yeah, thanks.
Thanks, Chris. There's one question from Jonas Helsen. Does the performance of the algorithm, both in the threshold and in decoding time, depend strongly on the choice of the sweep direction?
So yeah, that's an interesting question. We didn't really look at the sweep direction very much. So I mean, for these regular graphs, it shouldn't. Well, it's an interesting question. We didn't look at that very much. It's an interesting question. It could, and there's another question of there's some flexibility in the embedding. So as well as sweeping in a different direction, you could maybe try and adjust the graph to speed it up. Yeah, you could probably speed things up in that way. The thing that we really wanted to highlight was the flexibility, the fact that you can just throw a random graph into it and it will run. I'm certainly not suggesting it's very fast, but it's very flexible in that regard. So, yeah.
Okay. Thank you, Chris. So I think it's time, and let's move on to the next talk.
Thanks.
The third speaker is Antonio from the National Distance Education University in Spain, and he will talk about the thermalization in K-type quantum double models via tensor network techniques.
Okay, thank you very much. Can you hear me correctly?
Yes.
Okay, perfect. And can you see the slides also?
Yes, perfect.
Okay, perfect. So thank you very much to the organizers and also to everyone who is attending the talk. So I'm going to talk about a work which is related to the question of whether there are self-correcting memories in 2D. So let me remind that a self-correcting memory is simply a quantum system in which we can store quantum information so that it is preserved for long enough time without the need of external intervention. Now, the general belief is that in 2 dimensions, there are not self-correcting memories, and there are a bunch of negative results in this line. So in this work, we would like to focus on a specific family of topologically ordered systems called the quantum double models introduced by Kitaev. So here there were 2 previous results, one for the toric code obtained by Aliki, Fanes, and Horoteki, and an extended version for 1 billion quantum double models. And essentially the main result of our paper is to show that this negative result extends to all elements of the quantum double model using techniques that are different from those of the previous results. So let me briefly recall a little bit about the quantum double model. So we have a finite lattice on the torus with dimension n times n. We fix some finite group, and then at each edge, we fix some local Hilbert space, which is simply the group algebra. And now over this quantum spin system, we have a local Hamiltonian, which is made of 2 types of local operators, vertex operators and placket operators that commute with each other. So we let now our system to interact with a thermal path, and now we have to put some assumptions and using some theory of open quantum systems. And we can model the dynamics of our system in terms of a semigroup of CPTPs. Now this semigroup has a generator called the Davis generator. And I would like to focus attention on the so-called dissipative term of this generator. So it turns out that if we are able to show that the gap of this dissipative term is lower bounded by a positive constant independent of the system size, then this automatically yields that this system is not a self-correcting memory. This is precisely what Aliki, Fanes, and Horoteki proved for the toric code, and this is the main result that we obtain for the quantum double models. Okay, so I would like to briefly explain a little bit what are the ideas of the proof.
Antonio,
so yes.
Excuse me, we can only see your first slide.
What? Oh.
We can, yeah, it's only on the first slide being displayed.
Oh God. Okay, sorry. Oh, I don't know what's happening. Okay, let me try again. Okay, now?
Yeah, yes.
Okay,
Quantum
so,
double model, yes.
Okay, so
Okay.
let me go to this slide. As I was saying, we have our system, which is the quantum double model. We let it interact with an environment, and then the dynamics of the system are described by a quantum semigroup, which has a generator called the Davis generator. And now I would like to focus on the dissipative term of this generator. And it turns out, as I said before, that if we prove that the gap of this dissipative term is lower bounded by a positive constant independent of the system size, then we automatically get that this system is not a good self-correcting memory. Okay, so this is what Alikifanes and Horoteki prove for the toric code, and this is also the main result that we get for an arbitrary quantum double model. So I would like to briefly explain some of the ideas behind this proof. So the first step is using the properties of the Davis generator. We can transform this dissipative term into a local Hamiltonian whose unique ground state is the purification of the Gibbs state, and whose gap is essentially the same as the gap of the dissipative term. So the problem now is reduced to find a lower estimate of the gap of this new Hamiltonian that we call Davis Hamiltonian. And now instead of, so Alikifanes and Horoteki, what they do is to deal directly with this Hamiltonian, but we are going to use a different technique, which is ideas coming from tensor networks, in order to obtain this lower bound. So the first step is to consider the purification of the Gibbs state, and then find a PEPS description of it. So I'm going to use the operator point of view. And remember that this Hamiltonian of the system is made of local terms, which are vectors operators and placket operators that commute with each other. So this allows to rewrite this exponential as a product of local operators. And then for each of these local operators, we can find a tensor network description. Once we have these local tensors, now we fix on one edge, and then we look at all the tensors that act on that edge, and we contract them. And then the resulting tensor is the one that we are looking for. It is possible to give an explicit description of this tensor actually just using 3 parameters of the group, although it has 10 indices. Okay, so once we have this description, the next step is to construct the parent Hamiltonian associated to that PEPS and to compare it with the Davis Hamiltonian. So how do we construct the parent Hamiltonian? We consider a certain family of rectangles of a certain size. And then for each rectangle, we have an associate tensor, simply contracting the tensor on the edges, which we can see as a map going from the boundary to the bulk. We look at the image of this map, which is a vector space in the bulk. We consider the orthogonal projector, and then our parent Hamiltonian is sum of these, the orthogonal to these orthogonal projectors. So with this definition, it can be easily checked that the purification of the Gibbs state is a ground state of this Hamiltonian. But actually playing with the parameter n, if we take it large enough compared to the temperature, we can actually guarantee that this is the unique ground state of the Hamiltonian. Moreover, that the gap of the Davis Hamiltonian, which remember is the thing that we want to lower estimate, is lower bounded by the gap of the parent Hamiltonian times some constant independent of the system size. And also that the gap of the parent Hamiltonian is lower bounded by a constant that does not depend on the system size and not on the temperature. So combining the 2 last conditions, we already get what we wanted, this lower bound. And I would like to also explain a little bit, because probably the most delicate part of this argument is the last point, to show that the parent Hamiltonian of the gap of the PEPS is gapped. And for that, what we do is to analyze the so-called boundary states and to check that they satisfy some property called approximate factorization. So let me briefly explain what is this. So let's go back to the rectangles that we were considering before and the tensors, okay, that go from the boundary of the rectangle into the bulk. So the boundary state is defined in the following way. So we consider this tensor and its adjoint. Then we contract the physical indices. And what remains is an operator that goes from the boundary into the boundary. Now, finding an explicit description of this boundary operator is not easy, but what we can do is to show that if the size of if this rectangle is large enough, then it can be approximated in some sense by an object that is rather simple. Simple in the sense that it is going to be a tensor product of local operators. And moreover, it can be shown that these building blocks, these local operators, are independent of the rectangle. So these two properties together is what we call approximate factorization. And now what we have to do is to try to apply some recent results for general PEPs that connect the locality properties of the boundaries of this type of regions with the fact that the parent Hamiltonian is gapped. I mean, we cannot apply them directly because most of these results are done for injective PEPs or type of PEPs that do not fit with the PEPs we are dealing with. But we are able to adapt some of these ideas here and to get the final result. So I just referred to the whole paper that was released this morning in arXiv for more details. And if you have any question, thank you.
Okay, thank you, Antonio. Is there any questions from the audience?
I'm sorry for the technical problems.
Okay, it seems that we don't have any questions. So let me thank Antonio again, and let's move on to the next talk. The next speaker is Misha Woods from the ETH Zurich. He will talk about covariant quantum error correcting codes via reference frames. Let's welcome Misha.
Hi, thanks. Can you see my screen?
Yes, yes.
Okay, great. So let me just, I have two monitors plugged in and I've lost the mouse. 1 second. Here it is. So now I just go into presenter mode. Wait, let me display settings, swap. Yeah, okay, good. So now you can see it's fine, right? You can see the red screen. Okay.
Yes.
Mouse pointer. Okay, we're ready to go. Thanks for the nice introduction. I'll try to keep it fast because there's only 10 minutes. So this is joint work between Yushan Yang, Joe Renes, and myself, Misha Woods, at ETH in Zurich, and also Yinmo and Giulio Chirivella from the University of Hong Kong. Okay, so let me just say, so in a nutshell, what this talk is about is that there's a recently new approach, which is alternative to other approaches to quantum error correction, where we circumvent the famous Easton-Knill theorem, and this paper and talk is about recent developments in that. So since the main core of the idea is about circumventing the Easton-Knill theorem, the first thing to do is remind you all of the Easton-Knill theorem. Okay, so and for that we have to discuss this notion of local errors and transversal case. So imagine you have a quantum computer, and every red dot represents one physical qubit of the computer. So we can partition the qubits into blocks, and here I've illustrated 3 such blocks. And then the idea is that you can construct codes where we can construct errors which only touch one qubit in each block, which is local, so to speak. So for example, this error in one qubit will be correctable in this framework. This error will also be correctable because while it's over 3 qubits, it only touches one qubit in each block, so that's correctable. And errors which are not of this form would be not correctable. Of course, it's very important to apply gates also in quantum computation because that's how we apply, that's how we do the algorithms. So you can also ask under this kind of scheme where we can correct these types of errors, what kind of gates can we apply? And it doesn't take too much imagination to see that the types of gates we can apply and be able to correct those gates error occurs, or gates which run transversal to the code blocks. Namely, here's an illustration of the case of that form. Because if a local error, not local error, if an error occurs during the application of the gates, we can correct it because it's only one error in each code block. Okay, so with that, let me just say as well that these transversal gates satisfy this kind of covariance property where for these transversal gates, which I showed a minute ago on the previous slides, acting at the physical level, they commute, so to speak, with the encoding map, which I denote by epsilon. So in other words, if we apply at the logical level, if we encode that and then we apply some transversal gates, that should be the same as at the logical level, at first applying that transversal gate or an equivalent gate and then we encode it. Okay, so with that said, how many of these transversal gates can we have? Easton Keneal, quite a while ago now, proved the no-go theorem regarding this question. So they made two assumptions, namely that the code space is finite dimensional, and the code space is just a subspace of the physical space where we actually encode the quantum information related to the computation. And the second assumption is that we can correct local detectable errors. And these are just the errors of the type that I showed in the previous slide. And then what the theorem says is that if 1 and 2 are true, then the transversal gates cannot form a continuous set, nor can they form a universal set, and universal in the sense of universal computation. So you won't be able to do universal computation. Okay, so this is quite a major, let's say, hurdle for quantum error correction. At the moment, there are kind of the standard approach to quantum error correction circumvents this in the following way. So normally, it's one applies Clifford gate plus this so-called T gate, which form a universal set for quantum computation. And here, the circumvention is that the transversal gates in this set are not universal. And the transversal gates are the Clifford gates, or at least they can be applied transversely if one wishes. But the T gate is not transversal. So that's how this fits into that theorem. And that's also why people often hear as the T gate being the costly gate, as we've heard throughout many talks at TQC already, because it's also quite related to this idea that you can't apply transversally. So it's costly to do the error correction. Okay, but this talk won't be talking about this approach, but we'll be talking about it'll be about this other approach where we use reference frames coming from physics to circumvent Easton Keneal theorem in a different way. So, and in this approach, you can apply, all your gates will be transversal, so you can apply a gate. So the application of gates is not so much an issue from the perspective of error correction, but of course it comes with its own costs, which is what we want to analyze. So you can more or less divide the papers on this into two sets, because in the sense of how they circumvent the Easton Keneal theorem, because you can circumvent it in two different ways. And this paper from 2017 used these so-called idealized reference frames, which are perfect in some sense, of which I won't go into due to time constraints. But here the circumvention is that they're infinite dimensional, and therefore they use an infinite dimensional code space. And remember, that was one of the assumptions that you had to find dimensional code space. The other approach is to use finite dimensional reference frames, and here the circumvention is that you can't decode perfectly. So there's an error in the decoding. We have a finite dimensional code space, but there's no decoding. Okay, and you should also see this other paper, if you're interested in this, that came out at the same time by these authors, which also circumvents the Easton Keneal theorem in the same way, namely it allows for small error in decoding, but it just does so without the use of reference frame and other techniques. But they're both equally interesting. And you can see a joint talk about these in TQC 2019 if you're interested. There have also been various follow-up papers. Yeah. So, okay, with that, let us now concentrate on the actual approach in this paper, which is as follows. So, the encoding is like this. We take one qubit in logical state. We choose a gate from we selected the unitary from SUD at random according to the Haar measure, and then we apply the encoding, the subroutine encoder, because there's a subroutine encoder and decoder in this technique, and the subroutine decoder takes us from a 1 qubit logical space to an NP qubits physical space. We apply the unitary we picked from SUD at random, and then we add the reference frames. And every reference frame consists of 2n qubits. Okay? And we also apply this unitary to part. So we could get the following like this. And then the total qubits are the NP qubits of the subroutine plus the NR qubits of the reference frame. The final encoding map looks like this after this process, and Our encoding map, because of this time measure, has this nice property I was telling you earlier about universal gates, namely any gate from SVD that you could apply at the logical level has this covariant property with our covariance encoder, and thus the name covariant encoder. For the decoding, what we do is we measure the reference frames, okay, and then that basically collapses the integrand of the encoding map to one particular value of the integrand, where that particular value depends on the outcome of the measurement of the reference frames. And this is only approximate, and hence the error in the decoding. And then the decoding after this is relatively simple. We can just apply these unitaries and the subroutine decoder. This takes us back to the logical space, and the decoder looks like this. Okay, of course, as I said, it's approximate, so once we've encoded and decoded, there's a small error. We don't get back to where we started exactly, and we characterize that error with the diamond norm, and we also add in here some error channel as well, because of course we want to also see what happens when we have errors. And the whole point is the paper is to characterize this encoding error, this epsilon curve. Okay, so we look at erasure errors, so local erasure errors, which are both detectable errors and they erase all the information, right, of the system where the error fits. And within this thing, we look at two sub errors. We consider the weak error model, where we're guaranteed that at least just over half of the qubits are not erased on the physical level, and also at least one block. What's the one reference frame out of the many reference frames onto the qubits is also not erased. So all the rest can be erased. And what we prove in this error model that we prove an upper bound, which goes as 1 over the square in the number of reference frames qubits. That's important to see here. And we also then by we also derive a lower bound, which also has the same scaling. And the lower bound is universal in the sense it only depends on the symmetries of these covariance channels and not the fact of the reference frame. So this proves that one is reference frame approach is optimal within this framework, and it gives the scaling. And this also for the lower bound we improve, we tighten the results functions.
It's about time, so maybe.
Okay, yes. So I will just finish. I'll finish very quickly. So then we consider the strong error model, which is basically the same, but now the local errors can occur in an IID fashion. So there's some probability of any error occurring at any site. And basically, again, we prove upper bound and lower bounds. But here here the upper bound and lower bound are the same, but without the square. And again, the fact that the lower bound is universal, so it proves that reference frame is an optimal approach in this framework, given this stronger harsher error model. And this is the best you can do. So we have square versus linear scaling in the denominator. So it's like Heisenberg scaling versus Schottland scaling. Although remember that this is the optimal you can do because we proved that. Okay, so here is a summary, and I invite any questions.
Okay, since it's existing time, so I think we have to move on to the last talk of the session. Let me thank Misha again. So the last speaker is Lisa from Technical University of Munich. She will talk about oscillator to oscillator codes. Do not have a special.
Thank you.
Misha, can you?
Do I have to do something?
You have to share your screen.
How do I stop sharing? I'm not sure how to stop. More leave. I could leave. Maybe I just leave and come back because I'm not sure how to do it otherwise. Okay, I will leave and come back.
Okay, Lisa.
Okay.
Are you ready?
Yes.
Okay.
Can you see my screen?
Yes, I can see your screen.
Okay, very good. Good. So my contribution to this year's TQC has the title Oscillator to Oscillator Codes Do Not Have a Threshold, and it is based on a recent work together with Robert Koenig. And as the title already says, in this work, we were considered with the question whether so-called oscillator to oscillator codes could be useful for quantum fault tolerance in the sense that they have a threshold. And so these oscillator to oscillator codes, which were introduced by Noel, Girvin, and Young in 2020, encode bosonic modes into bosonic modes. And more precisely, if we have k bosonic modes in some arbitrary state psi, we want to encode it into n modes using a Gaussian encoding unitary US and n minus k auxiliary modes, which are each in the canonical one-mode Gottes monkey type prescale or TKP state, which in particular is a non-Gaussian resource. And we also note that the Gaussian encoding unitary US is in one-to-one correspondence with a symplectic matrix S. So now the reason why these codes are interesting for us lies within the word Gaussian, because so in the continuous variable setting, Gaussian operations kind of take the role of Clifford operations in the sense that they are usually easy to implement, but they are not sufficient for universal quantum computation. And what is also known is that continuous variable quantum information cannot be protected against naturally occurring noise, actually not even against Gaussian noise, using Gaussian states and operations only. But so now, the way that the codes proposed by Noel, Girvin, and Young are constructed, this yields a question whether these codes can actually circumvent these no-go theorems and therefore be used for quantum fault tolerance. Okay, so the setup that we consider consists of physical noise, which is IID Gaussian displacement noise, which is the paradigmatic noise example in the GKP setup. And we aim to recover using maximum likelihood error decoding. And the strategy of this decoder is to find the most likely error that have caused the syndrome given the error distribution, and then corrects for this most likely error. Okay, so now the resulting or effective noise channel is equivalent to a noise channel, actually a random displacement noise channel again, but now acting only on the logical mode. And the distribution of this channel can be described by a 2k dimensional random variable x. And now for a fixed epsilon bigger than 0, we say that the decoding was successful whenever this x belongs to an epsilon ball around your region in R2K. And now our main result tells us that the success probability is bounded from above by the probability mass with respect to a standard Gaussian of a ball around 0, whose radius only depends on epsilon, the squeezing of the encoding unitary US, and the standard deviation sigma of the physical Gaussian noise. And in particular, it does not depend on the number of physical modes n, which means that we cannot hope to get rid of this bound by just using more auxiliary modes. So here the S is the symplectic matrix corresponding to the encoding unitary US, and the squeezing is defined as the maximum symplectic eigenvalue of S, and it corresponds to the maximum amount of squeezing needed for any single mode in order to implement the encoding unitary US. And so the consequence of our bound is that in order for the success probability to be high, this ball needs to be big enough in order to include a 2k dimensional centered random, normal random variable, which has a norm which is close to square root of 2k with high probability. And therefore, the squeezing would have to grow as a square root of 2k over epsilon, which of course averages for epsilon going to 0. So as a consequence, we can say that oscillator to oscillator codes do not have a threshold for a physically meaningful, that is, bounded amount of squeezing. But they may nevertheless be useful for error reduction, as Nogiving and Yang already showed in the paper where they introduced the codes. Okay, so thank you. And please, if you have questions, let me know.
Okay, thank you, Lisa. Any questions from the audience? Okay, if no questions, then let me thank all the 5 speakers of this session for their great talks. And then we will have a break. And then the next session is the business session in 10 minutes. So we'll see you there. Thank you.
Hello. Just going to get my screen shared. So can everyone now see my screen and hear me?
Yeah.
Yes, I can hear you.
Great. Great. Okay. And I hope also see my screen.
Yes.
Good. Okay. So welcome to the TQC 2021 business meeting. This is our agenda for the day. So we're going to hear a report from the local organizing chair. Then we'll have a report from the PC chair, who will also present the outstanding paper prize. Then we'll have the announcement of TQC 2022. We'll talk about how you can propose a location for TQC 2023. And then we're going to have sort of the remaining time will be spent on a community discussion. So that's the point. You can already start thinking about if you have any kind of comments about TQC as a conference or any questions. We have one main thing we want to talk about, which is sort of the role of TQC with respect to QIP. Are these how are they different? How do they complement each other? But we'll also have time if there are other comments. So you can already start thinking about that. So yeah, to start off, I'd like to ask Andres if he can start us off by presenting the report from the local organizing committee.
Hello, everyone. Stacy, can you unshare your screen?
Yeah, there we go. That should.
It doesn't let me to share it. Okay. Let me share my screen. So this is the local organizing committee report. Originally, we intended that TQC 2021 would be an in-person conference. 1 year ago, idea was that we at University of Latvia organized TQC 2020. So the schedule for the following TQCs would be moved 1 year forward, and we would organize 2021 as an in-person conference. Unfortunately, this turned out to be still impossible. At some point, we thought about doing it as a hybrid conference, and then in March, we decided to go fully online. So as you saw, we did Zoom webinars for invited and contributed sessions. We also did a simultaneous broadcast on YouTube. In case if Zoom is not working for someone on YouTube. And this time we used Remoko for poster sessions and coffee breaks. So Remoko is a tool for virtual sessions that allows video chat and screen sharing and so on. So this was an experiment. This was a new platform. We thought that we wanted to try something more interactive than Slack for poster sessions, and we ended up choosing Remoko. As program committee chair will tell you, there was a record number of submissions. Having conference online apparently makes it much easier to present papers. So there was a huge number of submissions, and there are 78 accepted papers. So this ended up requiring major changes to schedule. So far, the typical number of TQC papers has been around 30. There were several options that we thought about. One idea was to make it a 5-day conference. A more major change would have been moving to parallel sessions, or we could do the option that we did, have recorded talks, and then short question and answer sessions. So short live talks plus longer recorded talks that interested people could watch. And we decided to go with this format because 5-day conference by itself would not have been enough. 78 papers is still a pretty big number. We didn't want to do parallel sessions, so the remaining option was to have long recorded talks and short live talks. And this is a format that is pretty common in theoretical computer science conferences. STOC, CCC, ICALP, and many others have been run in this way during the pandemic. Scheduling was another issue. Our conference starts at 10 a.m. in Latvia, which is 9 in Western and Central Europe, 8 in UK, 3 at night on US East Coast, and midnight on US West Coast. And then in the other direction, 10 in Latvia is 13:30 in India, 15 in China, 17 in Sydney. So we decided to have a morning session starting at 10, so that it would fit both Western and Central Europe and Asia and Far East. And then we have a somewhat late evening session that starts at 5 p.m. in Latvia, but would fit both Europe and North America. And for poster sessions and open problem sessions, we decided to have 2 copies of them. One in the morning and one in the evening to accommodate people people in Europe can attend pretty much all the events, and then people in Asia or North America can attend either morning part or the evening part. So here are the registration statistics. As of this morning, we had 445 registered participants from 37 countries. The countries with the largest number of participants are United States, India, Germany, China, United Kingdom, Canada, Japan, and Netherlands. And here is some actual attendance numbers. Similarly to TQC 2020, having 400 registered participants doesn't mean 400 people watching TQC on the same day. People register and then they might watch a few sessions on topics that are closer to what they are interested. So on Zoom, we had 155 distinct users, distinct email addresses. The number of people at the same time ranged from 17 to 55. So the largest numbers were for morning invited talk and afternoon open problem session, and the smallest numbers were at the end of day at 8:20 Latvian time, 7:20 Western European time. And there was also some substantial number of people watching on YouTube. So I would say that the YouTube numbers were slightly above half of the number of people on Zoom at the same time. And the recorded talks have gotten about 30-40 views on average. The largest number of views for the same recorded talk is 132. And the poster session today was attended by 72 people, about half of them authors and half of them attendees without poster. And in terms of budget, we decided to go with no registration fee, so that charging a small registration fee would not prevent people from signing up and listening to talks that they are interested in. And since conference was online, the costs were also pretty low. We paid 770 euros for software licenses.
Andres, I think we've lost you.
Maybe we didn't pay enough.
Since everyone's camera's off, I could not tell if it was me cutting out or Andres.
Yeah, I think it's Andreas. Okay.
We can just wait a minute and see if he comes back.
Okay. So the local organizer is reaching out to him. So,
but otherwise, maybe Minshu, you can be kind of ready to.
Yes. Yes, yeah, if you want me to go first, I can.
Yeah, maybe to keep up with the schedule, you could do your part now, and then we can continue with Andres after.
Okay, so let me share my screen.
Oh yeah, and let me introduce. Oh, actually.
Oh, he's back. Yeah, he's back. Okay.
Yeah.
Okay.
Yeah, sorry, my internet accidentally disconnected, but I'm almost finished with the presentation. Yeah, so this is the local organizing team. Елена Glusha, Mārtiņš Kokainis, Aleksandrs Rivas, Juris Smotrovs, Evgenijs Vichrovs. They all have contributed a lot of time and a lot of thanks to all of them. So out of 8 people, 7 are members of our research team, and Yelena is the communications and event organizing person for our faculty. So, well, this is all. If there are any questions, I'd be happy to answer.
Thanks a lot, Andres, for the report, and also thanks to you and the whole organizing committee for what I think has been so far a really great conference. Although I wasn't at TQC last year because I was on maternity leave, so I suppose maybe it was equally good. But I feel that this year's TQC does seem like it is being run by people with lots of experience running an online conference. So thanks a lot. Maybe if there are any questions, maybe we can also hold them until the end for the discussion. And now we can move on to the report from the PC chair. So Minshu, can you take it away?
Yes. So Andres, could you stop sharing so that I can? Okay, good. Oops. Just give me a second. Oops. Can everyone see my screen?
I cannot see your screen.
Okay, give me a second. Share now. How about now?
No, I can see your screen. Yeah.
Good.
Okay. Okay. Good. Thank you, Stacy. So now let me quickly walk you through the statistic of this year's submissions. Okay. So we have received 245 submissions plus 15 late poster submissions this year. If you compare with the number last year, there were 145 submissions in 2020. So there is about 70% increase this year. So each submission was handled by 3 PC members. As a result, more than 730 review reports were generated by the PC this year. Of course, some of them are with the help of sub-reviewers. And I would like to...
Sorry, can I interrupt for a second? I think
okay.
I think there's a bit of a distortion in the mic. Maybe it's a bit too close. It's coming from,
okay.
Yeah.
How about now?
That's actually
okay.
much better. Yeah, that's much better. Thanks.
Okay. Okay. So let me continue. So I would like to emphasize that each PC members has spent significant amount of effort to make sure that the reviewing score are normalized based on the quality in his pile, even if the sub-reviewers are used. And then we decided to accept 78 talks based on the report and the follow-up PC discussions. And so this leads to 33% acceptance rate this year. Overall, the TQC statistic this year can match I think it can match with QIP a few years back. And I'm very happy to see this conference has grown to this size and reputation as a PC chair. Here, I would like to give you an overview of how the reviewing scores distributed. You probably won't find this plot surprising because like around 10% of the submissions, you can see the score are above 2.0, and this would make it to a clear accept. So it requires less efforts for this range. And you can see then around 50 to 60% of the submissions are in between 0 and 2. And I would argue that the quality of the submission in this range did not differ significantly. However, we could only select 1/3 from this range. So you can imagine that almost all the efforts of PC discussions go into picking about like 1/3 of the paper in this range. And the selection at this stage is a bit random, I have to admit. It really depends on the PC's research interest, and also depends on whether someone stands strongly for a specific submission. So, I mean, if you receive positive report by wondering why your paper was not accepted as a talk, I think this might be the reason behind it. In addition, what makes TQC conference unique in our community is that it has a conference track and published proceedings. So this year in the conference track, we accept 10 papers. But I would like to emphasize that the reviewing scores of these 10 papers are on par with the talks in the workshop track. And I find this very satisfying. And I think this is because we have a larger amount of submission this year. So the proceedings has been published online by now. The reference information of the proceeding is provided here. And it was available with the URL right here. Hold on. Sorry. Oops. And then we also selected the outstanding paper award from the conference track, and I will announce it at the end of my presentation. So I hope you like the program this year. So this requires a huge amount of teamwork. I want to use this opportunity to thank all the PC members who voluntarily spend their free time for this job. The program committee this year consists of 33 members, so it is the largest PC in all years. The list of the members is given here, but I won't read out their names one by one. However, I would like to highlight some statistics in our compositions. Firstly, the PC members are geographically distributed roughly around America, Europe, and Asia Pacific. We have 13 members from America, 11 members from Asia Pacific, and 9 from Europe. Secondly, we have 5 female members this year. I'm not satisfying with this number and believe it should be improved in the future years. I also want to give my special thank you to Days Sastaka from the local organizing committee, who has helped so much in dealing with EG chair submission systems. Without her help, we won't be able to handle the review and announcing the results so smoothly. So thank you, Days. I knew that the program won't please everyone who submitted their work, and you might feel disappointed by your favorite result getting rejected. There's always plenty of room for improvement down under. I welcome any comments and feedback regarding the program this year, and I promise I will communicate these comments to future PC chair and local organizers. Before I hand my floor back to Stacy, I would announce the winner of the Outstanding Paper Award in my next slide. So the award goes to Quantum Time-Space Trade-off for Finding Multiple Collision Pair by Yasin and Frederick. So very nice job done. Big congratulations to both of you. Thank you very much. So back to you.
Thanks, Minchu, for that presentation, and congratulations to Yassine and Frederic for the outstanding paper award. And yeah, so thank you to Minchu and all of the PC for putting together an excellent program this year. I know that it was a very high workload as compared to other years, and I think the program committee did a really fantastic job.
Thank you.
Yeah, so moving on in the agenda, next we're going to hear from Eric Chitambar, who is going to announce TQC 2022.
Great, thank you, Stacy. Let me just. Okay, hello everyone. I'm very pleased to announce that TQC 2022 will be hosted at the University of Illinois in Urbana-Champaign. And I just take 2 minutes here to kind of tell you where that is in the world and also just some features of the conference location. So we are located in roughly central Illinois, and it's near Chicago. So specifically about 150 miles from Chicago, but it's easily accessible. You can make the drive down in 2.5 hours, or there's a train that takes about 3 hours with a few stops along the way. There's also a regional airport in Champaign, and that has direct flights to Chicago, Dallas, or Charlotte. Also, if you're not keen into flying into Chicago, you can fly into Indianapolis, which is actually closer, and that's in Indiana, the state to our east. Or you could fly into St. Louis and drive or take a train in. So the conference will be hosted on campus. We have a new conference center that was just built, and I don't believe it actually had any conferences yet. It was supposed to be kicked off last year, but due to the pandemic, it was not used. So we will be the first major conference there, to my knowledge. Hotel options are nearby the conference center. It's either there's a hotel directly connected to it, or there are other hotels around town. And it's nice. It's not a very crowded area in the summertime when the students aren't there, so it's easy to get around. There's shuttle and Uber services available. Yes, parking is easy and cheap. So the campus in Champaign has its own area of restaurants and nightclubs, but there's also a downtown Champaign, which is particularly nice in the summertime for sitting out and having dinner or having a drink. And so this is a nice place to go after a long day of an exciting day of science. So on behalf of the Illinois Quantum Information Science and Technology Center, which has 40+ faculty members, we welcome you next summer to come to Champaign-Urbana and enjoy TQC there.
Thanks a lot, Eric, and I'm definitely looking forward to seeing everyone at an in-person conference again. It will be nice to get back to those next year. If anyone was watching this and wondering, like, how could I host a TQC? That's what we're going to talk about next. You too could be the host of TQC 2023. So how do you apply to be host of TQC 2023? Well, we are soliciting proposals to host TQC 2023. These proposals should include a few basic elements. So the name and affiliation of the main organizers, like who you are, what would be the possible dates. We prefer to have the conference somewhere around July. A bit about the conference venue that you're proposing. So its location and size, any special features. And to give an idea, TQC, like the last few in-person TQCs, well, the last one in 2019 had 225 participants, which was more than in previous years. There's sort of a growing trend. So the last 3 in-person conferences had 107, 142, and 225 participants. So probably it would be good to prepare for a capacity of like up to 300 to be safe, I would say. And then you can also talk about any special features of the conference venue, travel information. So like, why is it easy to get there, good accommodation. So you can kind of put these in whatever format you think is appropriate and include any other special things that might convince us that your location is good for TQC. And we would like to receive these by October 15th. So I guess an important thing that is not on the slide is how you could actually submit such a proposal. So I will just put in the chat. So hopefully I didn't make any typos in this. So you can email TQC steering committee at googlegroups.com and with the subject line TQC 2023, your proposal by October 15th. We try to rotate the location of TQC between, I see, okay. Well, I see now a comment that YouTube viewers would not have seen my my chat with the email address. So I will add that you can also Google me, Stacy Jeffrey, and then you'll find out how to contact me. And it's also fine to just send me your proposal with the subject line TQC 2023 before October 15th. I think one of the organizers is going to maybe share this in the YouTube chat. Either way, so you can email me or the TQC steering committee before October 15th. So yeah, we try to rotate the location between like Europe and the Americas and Asia Pacific. So this year is Europe, next year is America, which would make us maybe favor a proposal from like outside of Europe and North America. But then we also, another consideration we have is that we try to not be located too close to QIP, and QIP will be in Asia in 2023. So I would say that we will consider proposals from anywhere, and the steering committee will have to decide what we think is most important. But maybe a proposal from outside of Europe, North America, and Asia might be able to make a good case. Yeah, and past TQCs have been in, well, before when we were having in-person conferences, the last ones were Maryland, Sydney, Paris, Berlin, Brussels, Singapore. So we have had quite a lot of locations, and you could maybe be the next one. Okay, so that's all I want to say on that. And the next thing we're going to get to is our community discussions. So the main topic that I want to discuss is the role of TQC in the field. Like, how is it different from QIP? How much should the two conferences overlap? But you know, a discussion of the specific question, I guess, could take arbitrarily long. So before we get into this discussion, maybe I'll just open up the floor if somebody wants to make a comment or ask a question. It can be about TQC in general, or it can be a question about anything you've seen. Like you can direct a question also at the PC chair or the local chair, or Eric, who's going to be next year's organizer. So does anyone have any questions or comments about TQC or any of these things? Okay, so I think that's I think there's not any general questions, so we'll move on to the specific discussion, which is the TQC versus QIP.
Stacy, there was a question.
There was a question.
In the chat, just posted, are the plans for online presence at conferences moving forward?
That's a very good question. And I think actually this this maybe also plays into a little bit the role of TQC versus QIP, because I mean, it could be that one niche for TQC is having like I guess that there has been a suggestion that we could keep some online presence, although that's also somewhat difficult in general for the organizers to organize a hybrid conference. So does anyone have any, like, so I'll just answer, like, from the perspective of the steering committee, we don't have any particular plans to keep an online presence moving forward, but maybe it's something that we should discuss. So does anyone else have any comments or opinions on this possibility? Okay, so maybe I don't see any comments on the specific issue. Maybe it's something we can also discuss more in the discussion about, like, what is TQC's niche that's coming up. I do see one question. I guess it's kind of a technical question. Oh, no, now Seb says Seb says, well, I like the hybrid, but not the compressed talks. So I guess like a hybrid format with actually full talks would maybe be, yeah. I mean, I also personally, I like the idea of people being able to participate who are not actually able to travel there for whatever reason. But I also think there's like a bit of a risk that if we make it hybrid, then it's just too easy for people to not attend. And then you, of course, lose out on a very important aspect of the conference. And then, so Mara suggests that we could just keep the streaming option in YouTube. And I mean, I also think that this is a little bit up to the local organizers, but because it's something that they have to implement. But I do think this is generally a good feature of any conference. Do any of the other, like, panelists have comments on this?
Yeah, I think it would be good to keep some online presence. I think this is something that we should probably leave for the next TQC local organizing committee to see whether they can do it as a hybrid conference or not. So, well, generally, hybrid conference is sort of double work. One has to do in-person part, and one has also to provide the online part. And the costs of filming and broadcast might differ a lot in different countries. I would think it's quite desirable, but the question is how much effort and money does that cost?
Yeah, I mean, I guess we could sort of encourage local organizers to do it, and maybe even in the future we could consider asking for this to be included in the proposals, whether or not you actually, I mean, I could even say that now, you're welcome to, in your proposal for hosting TQC 2023, talk about if you have any plans for making a hybrid conference where the talks are streamed, and then that is something that we can, of course, take into account when we're selecting the next location. But it's not a requirement at this point.
So I think handling the streaming on YouTube is certainly doable as a start. That's now easier to do maybe than it was 2 or 3 years ago.
So is there a plan to potentially incorporate something like that into TQC 2022, Eric?
Yeah, I will try to, without promising for certain right now, but I will definitely try to do that. Yeah.
Great. Are there any more comments on sort of hybrid? I'm just seeing if I'm missing anything in the chat.
Yeah, Seb, we'll have to look into that. I understand your point. Yeah, on Zoom it's fairly easy to do it, but for live talks, it's another hurdle.
There's also a comment from Mate, who says, yeah, so the PC chair had shared with us the feedback that maybe reaching out to authors during the review process in case there are doubts should be something that the PC does. And I mean, I know that this is something that, like, this sort of detail is generally left up to the PC chair, and it is something that is of course possible. And we will pass this on to future PC chairs that it can, of course, I mean, it's something that has to be coordinated, but of course it can improve the review process if you know, the PC chair reaches out to an author if there's some doubts about the paper. Of course, this can't guarantee that the paper is going to be perfectly understood. It can always be that, you know, an issue doesn't come up until sort of the end of the reviewing phase. And then, you know, even if there is communication with the author, there's not necessarily time to fully understand the issue. And as Min-Shu said, nobody claims that the PC does a perfect job. This is kind of not their job. It's not, you know, it's never a 100% fair process. That wouldn't be feasible. The PC sort of does the best to choose the best program that they can, and it's always going to be in some parts subjective, in some parts subject to a bit of noise. But certainly this would be something to try to do to improve the process where possible. But also authors should continue to try and make their paper as understandable as possible, so these rounds of communication are not necessary. But of course, this is misunderstandings can always come up. So yeah, so thanks for the comment. I think in the interest of time to actually discuss the main thing that we wanted to discuss, I want to move on to the topic of, like, you know, what is sort of the niche role of TQC? I think there was some discussion of this at the QIP business meeting. So, like, you know, should there be overlap between these two conferences? What is the difference? And I mean, I think the field is definitely big enough to have two quantum theory conferences, but I also think they don't have to be exactly the same. The most important difference, I think, is that TQC has proceedings. And so for people who don't know, proceedings are a publication of the results that are presented at a conference. And in the theoretical computer science community, proceedings publications are as important as journal publications. So it's common in theoretical computer science to first publish something rather quickly in the proceedings of a prestigious conference, and then later publish a more detailed journal version, which also goes through a longer review process. So for the theoretical computer science community, it's very nice to have a quantum conference that actually has proceedings, which QIP does not. Like, it's also, of course, we could also publish work in the proceedings of a non-quantum conference, but often the right audience that you actually want to present to is a quantum conference. So this is kind of a nice option to have, and this is something that differs from QIP. But we also understand that for other members of the community, publication in proceedings could actually preclude journal publication. And that's why we make proceedings publication optional by having the two tracks, the workshop track with no proceedings and the conference track with proceedings. So this is so that's one major difference. I mean, I guess the second difference is, well, like, TQC it's easier to get into than QIP. And I mean, this might not sound like a good defense of TQC, so maybe let me rephrase. Our field is growing a lot. It's getting quite big. And I mean, not everything will get into QIP. And I mean, it's great that QIP is so selective. It makes an excellent conference, but there's enough room in the field to have two excellent conferences of all of the top results. So I think that having
I propose that we wait a few minutes for Stacy to reconnect.
Sorry about that. So can someone let me know what is the last understandable thing that I said?
You said something about TQC not having proceedings and of good papers that are not being accepted in QIP and the field being large enough for 2 conferences.
Okay, yeah. So I guess my point there was that I think there we go. Yeah, I think that the acceptance rates are somewhat converging, and I could imagine that in a few years it might even be that you know, the conferences are sort of similar in prestige, and you know, you submit to whichever one is coming next. In any case, I think there's room in our field to have 2 quantum theory conferences. But yeah, what I would specifically like to pose as questions to the community is like, you know, do we want them to be more distinct? So for instance, should we implement restrictions on the overlap between TQC and QIP? Like right now, I mean, what we would not want to happen, of course, is that we have the same program happening twice, so that there's not any point in going to both conferences. That doesn't happen at the moment. There are overlaps. So sometimes that, you know, there are some talks that are accepted to both. We wouldn't necessarily want to actually implement restrictions. Like, for example, we wouldn't want to say that something that was presented at QIP cannot be presented at TQC, at least in the proceedings track, because we want to leave it open for authors of QIP papers to also be published in the TQC proceedings, since QIP does not have proceedings. And we also would probably not want the, you know, QIP to decide, well, we won't accept anything that has been presented at TQC, because I think this would be quite bad for TQC's submission numbers. So I would say, as long as there's no problem with too much overlap between the 2 programs, I wouldn't do anything. But if anyone has any sort of suggestions or ideas along these lines. And then the other question we could discuss is, you know, is there anything else that we should do to distinguish TQC and QIP? Is there like a niche in our field that is not being filled that maybe TQC should consider angling into? So I would like to open up to comments on this discussion in general, and in particular these 2 questions. Do any of the other panelists maybe have any thoughts on this?
I think on overlap it could go down naturally as conferences return to in-person format.
You mean because people won't want to travel to both of them?
Online format really makes it easier to give the same talk twice.
Mm-hmm.
So I think this is something that we could watch as the conferences return to in-person format and see whether the overlap goes down naturally or not.
So
and then for question 2, and then for question 2, I wonder, is there any natural space for more experimental work on quantum algorithms? Like, there is a fair amount of work, of less rigorous work on quantum machine learning that is attacking various problems in experimental way. And I think it's a valid line of research. So the question is there an outlet for such a work among conferences in our field? And should we become one? Well, if the answer to the first one is no, it doesn't necessarily mean that we should become, but I think this is one area that is not covered in either QIP or TQC.
Does anyone have any thoughts on that? I also see in the chat that there's a couple of points that I'll read. So Mars says he's not a big fan of the proceedings. Here's why. Normally the paper is already on arXiv, so having it published in proceedings doesn't add much value. It is extra work for the authors to shorten the paper for proceedings. The review process at a conference is not as thorough, so in the end, the quality of the proceedings is up to the authors. I mean, I guess I agree with some of this. Like, I do think that it is sort of, I guess, the tradition or the culture in theoretical computer science to publish in the proceedings, and I would much rather publish something that I think will be interesting to a quantum audience in TQC's proceedings than, fly to an extra conference where the audience actually is not interested in the work and just talk to a room that's just the other speakers of my session so that I can be published in those proceedings. But maybe that's just another argument against proceedings at all. So I think it's an interesting point. And then Sev mentions that departments use proceedings as publication count statistics, and whereas the arXiv does not count. And I mean, you might say that we shouldn't care about these things, but sometimes you have to be realistic, and some people, depending on your career stage, you might not have the luxury of not considering these sorts of things.
Like, okay, on proceedings, I agree with Stacy. I think if papers are published in proceedings as they are in computer science, then I find it more sensible to have TQC proceedings than in proceedings of TQC, as opposed to having 2 quantum papers in one non-quantum conference, 2 papers in another non-quantum conference, 2 papers in yet another one. So I think it's good to have all the papers, all the quantum papers that are published in computer science conference at the same place, or at least some substantial fraction of them. I think going to a general computer science conference with 4 quantum papers is a bit of waste of time.
Yeah, and I think I think that I guess you could again argue like that traveling to conferences just to have your work published in proceedings is just generally wasteful. But I think with TQC, most people are really actually motivated to go because they're interested in the talks, and so it's not that it's an extra trip. So I think that's much better than like if I publish something in the proceedings of just a CS conference, I probably also want to publish it or also want to present it at a quantum conference because that's probably the audience that cares about it. And there are a couple of comments about the overlap. If QIP doesn't put restrictions on overlap with TQC, the number of submissions shouldn't go down that much if TQC does. This is from Maris. So I kind of agree with this comment. I guess like TQC could restrict that you can't submit something that was already in QIP, but then I would not want to apply this to the proceedings track because, you know, people who have presented at QIP don't have their work in the proceedings, and so they might want to also have it in the TQC proceedings. And Misha says we could try to liaise with the QIP organizers to find out the overlap of participants to see if it's high or not, and this could help the organizers decide. So that's another good point. Like I would say right now, I don't think there is a problem with the conferences overlapping too much, but even if they do start to overlap, if the participants are distinct, it still might not matter that much, or as much, I guess. And now Mara says, I would like proceedings more if they didn't have length restriction and perhaps had an extra more thorough round of review, basically if it was like a journal publication. And I guess I would reply to that, like I do in the last few years, I think it has been the case because there's like TQC proceedings are relatively small since only a fraction of the TQC papers are actually in the proceedings. And therefore, I think that normally the publisher has been pretty lenient with the length restriction. So maybe you could see that as sort of a pro of these proceedings. But the extra round of review, I'm not sure how you would sort of orchestrate that. And I mean, I kind of agree, Maris, that like there's a bit of a problem with people submitting to conferences and where publishing in conference proceedings, where the review process necessarily is not as thorough as a journal because it's on a timeline, and then thinking they don't have to publish in a journal anymore. And then there ends up never being a journal version. So this is, I think, just like a problem that is sort of beyond the scope of just TQC's problem, but maybe we should all find ways of pressuring each other to actually get around to publishing journal versions of things. And Sev says about the proceedings length, it's a double-edged sword because CSers often want to flip to journal, and this is often not possible if the proceedings is the full version already. I guess that's also a good point. Your journal version is supposed to be somehow an extended version. Anyone else want to chime in with anything?
I guess maybe I'd like to second Andres' suggestion to maybe consider having a few experimental papers on quantum algorithms to kind of differentiate ourselves from QIP. I think that is a growing area as well. So that's something that we want to keep an eye on, and an exciting field as well. So that might be something to focus on more in the future, or at least accept a few more submissions.
Maybe I'll also comment that, so I'm also on the steering committee of QCrypt, and where they accept papers in like quantum cryptography papers in both theory and experiment. So it is possible, but like a lot of effort has to go into this. So like the program committee has usually the co-chair is from experiment and the chair is from theory, and they try to have like a balance of people from both, because it's, of course, I would say that probably the program committees from the last few years would probably not be super well equipped to evaluate experimental papers. But maybe it's something that we could think about how we could implement something like this.
Yeah.
And then they would also, of course, we would have to make sure that the talks were really geared towards an audience that is mostly not on the experiment side, and they would have to be made understandable. And Maris suggests renaming TQC to QIP. I'm not sure I agree with that suggestion, Maris. I don't know if anyone else has any opinions on that. Yeah, Maris says he's going to keep advocating to change TQC to QIP next year. Oh, okay. So there's maybe separate Q&A, which I was not monitoring. So that's my bad. Sorry about that. So questions from the Q&A. Yeah, there's one question about online versus hybrid, and a couple more comments about online. I think we've addressed that, but please ask if there's anything more that we should talk about. And okay, now there's some comments coming in.
Okay, I think I know what question Evgenis is talking about. So there was a question about having poster sessions along the lines of stock, where every talk is presented both as talk and as a poster. I guess it's somewhat unusual format, and we can discuss it.
Was this Andres? Were you addressing Alexander's question, or saying I'll just maybe it's not for public discussion now, just some random thoughts. Last two TQC's Latvian team managed somehow to make an event with no registration fee. I have a feeling we all are entering the golden age of quantum computing and other quantum tech, and I wonder, can we maybe, with the generous help of sponsors, keep registration fees low enough to make TQC accessible also for students from not so rich countries? I'm not thinking about my country anymore, but some of us still remember how hard it was once upon a time. Travel plus accommodation expenses are already challenging enough for quite a large part of the world. I guess like generally this is something that is up to the local organizers, but I think it's like it is a good idea to try and have also, if possible, from sponsorship funding for students. And maybe this is something to talk about in proposals for future TQCs. But another thing is like there could also be, if there's a part of the conference, like if the conference is streamed, that does open up a possibility of at least following the conference without even needing funding to travel there. So that's one thing. And maybe when we're thinking about like future hybrid implementations, there can also even be like some virtual events that has a little bit of the meeting up with people aspect for the people who are kind of following the conference virtually, but not actually participating in person. So I think this is definitely something to think about, because one of the huge appeals of virtual conferences is that there's not a financial barrier to joining. Okay, I think maybe that's a good place to end on time. So thanks again to the local organizers for what is so far turning out to be a great conference, and to the program committee for putting together such a nice program for us, and also to everyone who's giving a talk or participating in the conference. So with that, I will end the business meeting. Thanks a lot, everyone, and see you at the next invited talk.
Thank you.
Thank you.
So you can hear me, right?
Yeah.
Okay, great.
Okay, hello everyone, and welcome to this session for the invited talk by Srinivasa Arunachalam. He's got his master's degree from University of Waterloo and his PhD from QSoft at Netherlands. After that, he was a postdoctoral research at MIT, and currently he is a research staff member at IBM T.J. Watson Research Center. Okay, so today he will be talking about results for learning quantum states. And the time is yours.
Hey, thanks for the intro. Thanks for coming for my talk. Good morning, good afternoon, and good evening, wherever you are. Firstly, I'd like to thank the organizers for organizing this wonderful conference. It's an honor to be speaking here. Thanks for giving me this opportunity. So today I'll talk a little bit about learning quantum states. So my talk is going to be slightly different from what I said in my abstract. So my abstract said I'll talk about 2 results, but then I just thought maybe let me just overview what are some recent results on learning quantum states. Right. So let me begin. Right. So recently, there's been a lot of interest in quantum machine learning. There's received tremendous attention because quantum is exciting, machine learning is exciting. There's a lot of interesting things that can happen. But one thing that's happening is the more we try to understand what's going on, more we realize that getting large quantum speedups is not that simple. It's actually much harder than we expected. At least getting exponential speedups for some genuinely interesting problems is actually not that easy as what we thought it to be. But then there's been a lot of work still in this field, like even to understand what's going on, what are the promising directions. And the last few years, there have been some works in this direction. For example, there have been some works on obtaining quantum algorithms for classical problems. For example, like people have looked at a lot of optimization problems, say like linear programs, convex optimization, SDPs, gradient descent. And in these problems, people have given like some quadratic or polynomial speedups, which is still exciting. And in another direction, there's also been a lot of classical algorithms for quantum problems. And what I mean by that is, let's just say, for example, you have a parameterized quantum circuit, and people call it quantum neural networks. So like you have this quantum circuit with unknown gates, with each gate having a parameter theta. Say you can only observe input-output statistics, and based on these input-output statistics, you run a classical gradient descent to learn these unknown angle thetas. So that is one thing. And there's also been, like, for example, like you have a noisy quantum system, you would like to understand the noise model in the system. So you look at input-output statistics and use some classical ML model to understand what's the noise in the system. And the final thing which I've been very much interested in the past is trying to just learn classical Boolean functions. So let's just say you have a classical Boolean function, say it has a concise description, say it can be described by a polynomial size classical circuit. Can we learn these class of functions in the quantum model? And as I said before, the promise or the algorithms in this model, they either promise like a polynomial or exponential speedups, but everything comes with certain assumptions. Like, for example, some assume like quantum examples, some assume some quantum RAM or quantum oracle access and things like that. But they're still in these models, which are explicitly stated, you can get some form of quantum speedups. But today, what I'll be talking about is learning quantum states. So like, for example, like I'll try to look at quantum algorithms for quantum problems. So learning quantum states, and this has received a lot of attention also in the past few years, maybe even decades. And the more attention that's achieved is mostly in the numerical side or in the theoretical side. But one thing that's been happening the last 5 to 10 years is many works are heuristic and they promise fast algorithms, but showing that they can provably work is a hard problem. So many of these heuristic algorithms, they run it on like quantum simulators, and it seems like they do perform well, but proving that they actually perform well by asymptotically, it's not that easy. And that's going to be the focus of my talks is, can we learn quantum states with provable guarantees? Right. So let me quickly overview what I'm going to be talking about, at least the 4 topics I'm going to be talking about. So I'm going to be, in the entire talk, I'm going to be learning rho, which is an unknown quantum state. And in the standard well-known model, you're given copies of rho, and you need to learn rho, and that's the standard tomography problem. So I'll talk about this. I'll briefly highlight what it is and what is the result that we have there. And the next thing is, let's just say you're not given copies of rho, but you're just given measurement statistics of rho. And can we learn rho approximately? Well, this is the packed learning model, and there's online learning, and there's some equivalences between all these learning models, which I'll talk about. Then I'll talk about you're given copies of rho, but then you only need to learn rho with respect to certain measurements. Like tomography wants to learn rho completely, but let's say you want to learn rho with just certain measurements. And this is a tomography problem, and there's some variants of this. And finally, the first three topics are going to be just about learning models and what can we do for arbitrary rho. The fourth topic, I'm going to be looking at learning rho for an interesting class of rhos, or interesting class of quantum states. Can we learn them? I'll talk about learning Gibbs states of local Hamiltonians, stabilizer states, and their variants. And since my talk is going to be mostly like an overview talk, I'm not going to go very much into the details of the proofs. I'll just give you like proof sketches here and there, or more or less, I'm going to tell you what are the results in this direction, and I'll conclude with many open questions. Right. So part one, let me start talking of learning models and what do we know in these learning models. So first thing, let me talk of tomography. So let rho be an n-qubit quantum state. So rho is like a complex positive semi-definite trace one Hermitian matrix, which is d by d, where d is 2 to the n, because rho is an n-qubit quantum state. And the question in tomography is how many copies of rho? So somebody keeps handing me copies of rho. How many copies of them are necessary and sufficient to produce a classical description of the state, produce a state sigma that approximates rho well enough? So putting it pictorially, somebody keeps giving me copies of quantum state rho, or t-fold tensor copy rho, and the goal of QA, or quantum algorithm, is to produce a state sigma, which is approximately close to rho. This approximation is important. For now, you can think of it as a trace distance approximation. And this is a very fundamental question. I mean, it's just so fundamental that in quantum, like if we come, let's just say somebody builds a quantum computer and they say we can prepare the state rho. How can you be so sure that they're preparing the state rho? You can do tomography. So it's just a very fundamental question in quantum computing, tomography. And there's a trivial algorithm to solve tomography, and that uses like d to the 4 copies of rho. So if you take d to the 4 copies of this unknown quantum state, you can kind of using some basic empirical analysis show that this learns a quantum state rho, or you can produce a state sigma, which is close to rho. And there was some recent work, not recent, like in 2013 or 2014, there was some work that improved d to the 4 to d cubed. But fundamentally, the question was, rho has only d square entries. Can we do tomography in d square copies? So this was a long-standing open question and a huge breakthrough in 2015 by Ryan O'Donnell and John Wright and John Wan Ha et al. What they showed is you can actually do tomography in complexity d square. So given d square copies of rho, rho has only d square degrees of freedom even, you can produce a state sigma that is trace distance close to rho. And not only is this an upper bound, they also showed that this is a lower bound as well. So you cannot improve the complexity of tomography more than d squared. So d squared is the actual upper and lower bound for tomography. But of course, d squared is very expensive, right? I mean, you can think about, for example, like if d is just, n is just 10, so you want to learn a 10 qubit quantum state, d is already like 2 to the 10, and d squared is approximately 2 to the 20. So just to learn a 10 qubit quantum state, we require 2 to the 20 copies of rho. And producing even like the same copy of rho in experimentally is not that easy. So producing many copies is just like experimentally infeasible. But there has been some experimental work a few years back that showed you can do tomography on 10 qubit quantum states, and this is the record so far. But this kind of motivates the question, maybe learning rho or producing a state sigma is maybe an overkill. Maybe you just want to learn rho, certain aspects of rho. You don't want to learn rho almost entry-wise well. You don't need to output a description of sigma, which is very close to rho, but maybe you just want to learn certain aspects of rho. So this motivates this fundamental question, can we propose alternate learning models which only captures the fact that we learn certain aspects of rho? And in this way, the first learning model I'm going to be talking about is the packed learning model, or the probably approximately correct learning model. And right, so far we spoke about tomography, where we learned the entire quantum state rho. And one way to view the trace distance I spoke about in the previous slide is, let's just say I produce a state sigma, which is trace distance close to rho. That means in some sense, what I've done is I kind of approximated trace of E times rho for every E. So for every measurement, trace of E times sigma is close to trace of E times rho. So for every E, I can actually produce what is trace of E times rho. But maybe can we relax this goal? Maybe I don't need to do well under every E. Maybe it suffices to predict rho only under most E's. So only under most 2 outcome measurements, I want to learn what is trace of E times rho, not for every single trace of E times rho. And this is what motivates the question, pack learning. Right, so pack learning quantum states was motivated by classical pack learning. And the classical pack learning was actually introduced by Leslie Valiant in his work in 1984, where he gave a complexity theoretic definition of what it means to learn. And in this vein, he introduced the pack model of learning. And he said, like, if you can learn in the pack model of learning, that's a justifiable and theoretical framework in which you can say that a class of functions is learnable. And we can port this classical definition to the quantum definition as what I'll define next. Right, so here you have a quantum algorithm, and it just gives you, like, you're given like measurement statistics. So in some sense, there is a distribution D on all possible 2 outcome measurements. Script E is the class of all possible 2 outcome measurements. And somebody keeps sampling E1 to EK from this distribution D over all possible 2 outcome measurements. Someone samples K different measurements from this distribution and gives you trace of row E1 to trace of row EK. So pictorially, you're given E1, trace of row E1, all the way to EK, trace of row EK. That's given to a quantum algorithm, and it still needs to produce a state sigma, so the sigma is close to rho. But this closeness is going to be defined now. And the goal is to produce a state sigma that satisfies the following. So with good probability, where this outer probability is over the measurements, you need to produce a state sigma, so the trace of rho E is close to trace of sigma E. So recall, if supposing delta was 0, that means for almost all measurements, I need to do well. But the point is here, I'm going to relax it a bit. I want to say for most measurements, I want to produce a sigma that is close to rho with respect to that measurement. In other words, with probability at least 1 minus delta, where the probability is taken over the distribution D, I would like to produce a state sigma such that trace of rho E is close to trace of rho sigma, sigma E. So that's the goal of pack learning. So it's slightly different. You're no longer given copies of rho. You're just given measurement statistics, E, trace of rho E. There's this unknown distribution, and you would like to produce the state sigma such that it agrees with trace of rho E for most E's. I've just succinctly written it on top so that you recall the definition. And the fundamental question is, in this new learning model, can pack learning complexity be much smaller than tomography complexity? And the answer is yes. So in a wonderful work that Scott Aronson did back in 2003, he showed that you can actually pack learn a quantum state in just log D many examples. So it's exponentially better than tomography. So instead of D squared, you can do it in log D complexity. And it's a very beautiful result. And let me give you a quick proof sketch of this result of Scott. And the idea is pretty simple. He just says, take log D many examples. When I mean by examples, I mean EI, trace of rho EI, where K is log D now. And he says, go to your lab and just find a sigma that is consistent with these trace measurement outcomes and just output that sigma. But of course, like, it's not even clear why this works. Like, why should just taking log D examples suffice for you to produce a sigma that agrees with rho on most measurement outcomes? And the answer is there's this beautiful theory by BC theory for real valued functions. Let me quickly tell you what I mean by that. So consider the following function. So let f rho be a function associated to rho that maps all possible 2 outcome measurements to a real number between 0 and 1. And it's defined as f rho of E is equal to trace of rho times E. So because this is a probability, this is a number between 0 and 1. And let's look at the class of functions f rho from the class of all possible 2 outcome measurements to 0, 1, each function for 1 rho. So in another way, you can say learning rho is equivalent to learning this real valued concept class. And then now you can go back to classical learning theory and ask, what do we know about classical learning theory for real valued functions? And they have beautifully characterized that you can learn a real valued concept class. It's characterized by something called a fat shattering dimension. So it's just a purely combinatorial dimension. So if I understand this combinatorial dimension, it gives me an upper bound on the number of examples for learning this real valued concept class. And Scott then showed that you can, using ideas from random access codes by Umbinus and others, you can actually show that the fat shattering dimension of the real valued concept class is at most log D, and putting together with the second last bullet that shows that log D many examples suffice to learn this real valued concept class, which in turn means you can pack learn arbitrary quantum states. So this is the proof of what Scott showed. So to summarize, if you want to do packed learning quantum states, which is slightly weaker than tomography, you can get an exponential saving, but this comes at the cost that this is still time inefficient. The sample complexity is exponentially better, the time complexity is still large because of step one, where you need to find a sigma in your lab that is consistent. And just finding a sigma means going through the space of all D by D matrices. So this was packed learning. Great. And then subsequently, people introduce online learning. And first question is there a notion of even complexity theoretic notion of online learning? And there is actually. And this was introduced by classical learning theory people, where they said, in packed learning, there's this unknown distribution over two outcome measurements. But maybe it's not clear what this distribution is doing and why we care about it. And so they introduced online learning where there is no longer a distribution, but it's now a game between an adversary and learner. And in this game, the learner is supposed to learn an unknown quantum state, and the adversary is supposed to not help the learner. So in the worst case setting, we would like the learner to do a good job. Right, so let me define what this game is. So there's an adversary and there's a learner. So learner still needs to learn an unknown quantum state rho, but he doesn't know what rho is. He or she doesn't know what the rho is. And the learning happens in rounds. So in every round, the learner kind of has a hypothesis sigma, which is its guess of what rho is. So for example, sigma 1 is just identity because it absolutely doesn't know what rho is at all. So it just assumes that it could be one of all possible quantum states, the maximally mixed state. And the learning happens in rounds, and in each round, it keeps updating its hypothesis in the following sense. So first, in every round, the adversary presents a measurement EI. And the goal of the learner, and what the learner does, it replies with trace of sigma I times EI. So sigma I is the guess of the learner in the ith round. And the goal is the following. Trace of sigma I EI should be close to trace of rho times EI. That's the hope of the learner. And if that were true, then the adversary says, okay, sigma I is close to rho with respect to EI. But if sigma I EI is very far from trace of rho times EI, by which I mean it's epsilon far away in trace distance, then the adversary says you made a mistake. And once the adversary says you made a mistake, the learner updates its hypothesis. So it knows that sigma I and rho differ by quite a bit with respect to EI. So it updates sigma I to sigma I plus 1, where now sigma I plus 1 does a good job on the measurement EI. And this process keeps happening for many rounds. And as before, the goal is with as few mistakes as possible, the learner should output a sigma, like after say T rounds, the learner should output a quantum state sigma that does approximately well on all future rounds. So the goal is still same as like in packed learning. You produce a quantum state sigma that on all future rounds, trace of sigma times rho, trace of sigma times E is close to trace of rho times E for most measurements. So you're going to be correct for always. And there was this beautiful work from like last year or a couple of years back by Aronson, Chen, Hazan, and Nayak, where they showed that you can quantum online learn arbitrary states, making just log D many measurements. So this is still, again, another way to view that it's exponentially better than tomography. You can learn a quantum state in a different learning model. There's the online learning model, which is still exponentially better than actually doing it in tomography. And I'm not going to give you a proof sketch of this, but the idea is pretty similar to what was happening in packed learning. And the idea was to use this post-selected learning technique that Scott introduced back in 2003. And they not only did they use that technique, they also followed it up with a new upper bound on random access codes, a probabilistic random access codes. So putting together these two techniques, they obtained this result. So this is online learning, another learning model in which we saw that log D complexity suffices to learn an unknown quantum state, similar to packed learning, and both these models were exponentially better than tomography. Right. So of course, that kind of begs the question, is there kind of some sort of equivalence between these learning models? So we saw packed learning and we saw online learning. And one other thing that we looked at was, so Aronson and Rosblum, they introduced this notion of differential privacy for learning quantum states. So we didn't look at their model of learning, but motivated by their notion of differential privacy, we also considered differentially private packed learning. So we we require a learner not just to be packed learner, but we also require the learner to remain differentially private. I'm not going to define differentially private, but it just means like the differentially private just means that a learner given to databases that just differ by one element in the database, the learner should behave almost the same. So you would like the learner not to be able to distinguish different databases based on privacy arguments. Right. And the one question that we tried to understand was what states can we differentially privately learn in the pack setting? This was studied pretty well in the classical setting, but so far in the quantum setting, it wasn't studied. And that was one thing that we looked at. What can we learn in the pack setting in a differentially private way? And this was a talk that Yihui gave yesterday at TQC. It was the final talk of the day, where we showed various information theoretic equivalences between various learning models. And in particular, what we showed is the following diagram. So, I mean, maybe you don't need to understand everything in this diagram, but maybe the starting and the end point of this diagram is just differential privacy. So what we showed is everything in the middle is very much related to what can you differentially privately learn. There are, of course, many nuances and subtleties here. For example, this is pure and this is approximate and so on. But just superficially, the takeaway should be most of the things in the middle, which includes online learning, which includes fat shattering dimension, one-way communication complexity, packed learning. All these models are actually very much intricately related to what can you pack learn in a differentially private way. I'm not going to be talking about the proof of this diagram. I refer you to Yihui's talk, but I'll just make a few remarks here. The first thing is all these implications just are in information theoretic way. And what I mean by that is, let's say, for example, representation dimension is some number t that implies that dp pack complexity is poly of t. So all these arrows involve only a polynomial overhead, which is as optimal as you can get, except this one arrow star. And the crucial idea that we used in this improving this set of arrows is the connection that Scott also used back in proving packed learning. If you want to learn an unknown quantum state rho, you can associate a real valued function to it. And this real valued function, you try to go to classical learning theory people and ask them, what can you do for learning real valued functions? And if they have some positive result there, force it to prove quantum results. And that was kind of what we did here. Many of these results were proven in the classical setting for Boolean functions. For real valued functions, we extended their results. But one surprising result that we had was we proved that the final result, which was known for classical Boolean functions, is true for classical Boolean functions, doesn't hold true for real valued functions. So with the help of Mark Bunn, what we showed is we gave a concept class for which stability implies dp pack in the Boolean setting, but in the real valued setting, it was not. It's not known to be true. And this was classically new. So in some sense, like kind of the motivation was quantum learning, but we kind of had some new observation which even contributed to the classical learning theory for real valued functions. So I thought that was a kind of interesting perspective. Right. Right. So far what we spoke about is just learning. We spoke about packed learning, online learning, various equivalences between them. And in all these learning models, you had to learn an unknown quantum state with respect to a distribution of measurements or with respect to just like most measurements. Now I'm going to be talking about shadow tomography. And this is slightly different from the spirit of the first three models. We estimated rho so far on a distribution of measurements, but let's say we fix a set of measurements, can we learn faster? Let's say, for example, we are still given copies of rho, but additionally, we are given E1 to EK, the fixed K measurements. The quantum algorithm needs to only learn rho. He needs to produce a sigma, so the trace of sigma times EI is close to trace of rho times EI, only for the i's E1 to EK. So only for these K measurements, we want the quantum algorithm to do well. For rest of them, we don't care. Right, so this was shadow tomography, and this was introduced by Scott Aronson. So again, let me redefine. You're given E1 to EK. How many copies of rho suffice to estimate trace of rho E1 to trace of rho EK? And of course, there are two trivial strategies to solve this problem. One is tomography. And tomography just says take d squared copies of rho and just learn the unknown quantum state completely, which means that not only have you learned E1 to EK, but you have learned rho with respect to all measurements. And then just output trace of rho sigma E1 to trace of sigma EK, and you've promised you're doing a good job. But the complexity of tomography is the d square, which is very expensive. There's another strategy, which is an empirical estimator. So just take 1/epsilon² copies of rho and just estimate, just by flipping a coin, you can compute trace of rho times EI. You can compute trace of rho times EI for 1 EI using 1/epsilon² copies of rho, and to do it for E1 to EK, that takes k/epsilon² copies of rho. So these are two trivial algorithms for shadow tomography. Right, but what happened was that Scott looked at this problem in 2017 and he says like, okay, you can use ideas from online learning and packed learning, and you can actually estimate trace of rho E1 to rho EK in complexity at scales of log K and log D. I'm hiding polynomial factors, I'll come to it in the next slide, but it's polynomial in log K and log D, which is exponentially better than this K here and exponentially better than this in this D square here. So you can actually solve shadow tomography by just taking polylog of K and D many copies of rho, which is very surprising. And let me quickly give you what was the protocol, and also like I'll tell you what these polynomial factors are. So Scott's protocol was the following. His idea was again to go back to his very nice result that he had in 2003 of post-selected learning. So let's just consider the following two-party problem. So Alice has a quantum state rho, Bob has E1 to EK, and the goal of Bob is to approximate trace of rho EI, but only Alice is allowed to communicate with Bob. So Alice knows everything, Bob only has K measurements, and the point is Alice just needs to tell him what this thing is. And the question is, can you do better than K? And of course, the way this process works is similar to online learning. Bob's initial guess is, okay, rho is just a maximally mixed state. And Alice keeps giving Bob information such that he keeps improving his initial guess. So he has a sigma 1, sigma 2, and he keeps going in many rounds after Alice keeps sending bits. And after T rounds, Bob's hope is he should have a sigma such that trace of sigma EI is close to trace of rho EI. And then he just outputs trace of sigma EI for E1 to EK. Great. And the beautiful result that Scott had from back in the day was it suffices to just send poly of log D, log K many bits. So trivial upper bound would have been, again, tomography or just send K bits. But Scott showed that in the communication model, it suffices to send log D times log K many bits. So this was the idea that he had from back in the day, but this still doesn't suffice for tomography because kind of like there is no Alice in shadow tomography. There is just a Bob and he's just given copies of rho. Here, Alice could actually help Bob in finding trace of rho E1 to trace of rho EK, but in shadow tomography, there is no help. There's nobody to help Bob. He just gets copies of rho. He needs to produce this trace of rho E1 to trace of rho EK. And that's why there's some extra work to be done. So in this result of Aronson, he had a new OR lemma. And based on this new OR lemma, he actually goes from this communication protocol from steps 1 to 3 to actually obtaining a shadow tomography protocol. Of course, there's a lot more work that goes on, but I don't have time to talk about it. Also, this is just a very quick sketch of what's happening in the shadow tomography protocol. And overall, the complexity that Scott has with this protocol is log K to the 4, log D times 1/epsilon to the 5. So this was the sample complexity that he had for shadow tomography. And let me make a few quick remarks. There have been quite a few follow-up works after the work of Scott trying to improve the dependence on these parameters. And as far as I'm aware, the state-of-the-art result is by Costin Barasco and Ryan O'Donnell from last year, where they have the dependence, I think it's the best dependence on all parameters simultaneously, where they have log square K, log D, and epsilon to the -4. And it's an interesting open question, what is the right complexity of shadow tomography? And one thing that I haven't spoken about so far is this is all the sample complexity, what's the time complexity? And the protocol from 1 to 4, this is highly time efficient. But there have been some works by Brandau et al. And Appledon and Gillian, where they gave new SDP techniques to actually improve the time complexity of the protocol of shadow tomography. And also recently, there's been this work of Richard Kyung and John Preskill, where they considered learning classical shadows. So they said, like, for example, E1 to EK, for example, they are succinct measurements. What they show is they show log K many measurement statistics, which is independent of log D even, are sufficient to predict K linear functions of rho. So for example, E1 to EK, they are supposing they're just poly observables, then it's very nice. And I will use this result of HKP again, the second part of the talk. Right, so that I think concludes the first part of the talk, and I'm moving to the second part of the talk. And right. So the first part of the talk, what I looked at was learning. I looked at learning models, pack learning, shadow tomography, online learning. And I said, in these learning models, I can learn a bunch of quantum states. But the point is, let's say if I want to learn a specific class of quantum states, can I learn them maybe time efficiently? And the first thing I'm going to be looking at is the Hamiltonian learning problem. And this Hamiltonian learning problem, you're given Gibbs states of a Hamiltonian, your goal is to learn the Hamiltonian. So let me be slightly more clear. So let H be a k-local Hamiltonian on n qubits. And let's say, for example, we write H, or the unknown Hamiltonian, in an orthonormal k-local basis, E1 to En. You can think of M to be n. I'm going to be thinking of spatially local Hamiltonians. Then the Gibbs state at an inverse temperature beta is given by the quantum state rho, which is e to the minus beta h divided by the trace of it. The trace of it is the partition function. And the question is, given t copies of the Gibbs state, can we learn the coefficients of this Hamiltonian? So the quantum state hides this unknown Hamiltonian H. H has this poly, you can think of EI as a poly basis. So H has a poly decomposition. And the goal is to learn these unknown coefficients up to small L2 error. And the motivation for this, there are manifold motivation for this. Like, for example, like there's a physics perspective of this. Let's just say, for example, somebody gives you a Gibbs state and you would like to learn, for example, its conductivity and properties about this. How would you do it? You can solve the Hamiltonian learning problem. And recently, for example, all these SDP algorithms by Brandau, De Wolf, and others, many they involve a lot of quantum SDP solvers. They involve a lot of Gibbs states. And so you require copies of Gibbs state, but how do you verify that if somebody implements it, they're actually preparing the Gibbs states of the matrix that you care about? One way to do the verification task is again by Hamiltonian learning problem. In machine learning, people have looked at learning icing models a lot. And one way to learn the quantum icing model learning problem is precisely the learning Hamiltonians model problem. So there's a lot of experimental motivation and things like that for this problem. So we looked at this last year, and the main result that we had is it suffices for the number of copies to solve the Hamiltonian learning problem is polynomial in 1 over beta, 1 over epsilon, and n, and is exponential in beta and kappa. So I'll come to this exponential factor later, but the thing to realize is, although the quantum state is living in a 2 to the n by 2 to the n space, the sample complexity of the Hamiltonian learning problem is polynomial in n, and n again was polylog in d. So earlier I said d was 2 to the n, so again here n is log d. Right, so the sample complexity of a Hamiltonian learning problem is polylog in the dimension. And I can quickly tell you what's happening in the algorithm. What the algorithm is actually pretty simple. The state, proving it works is the hard part. Again, the problem is on the top and the complexity is the result is here. And the algorithm is pretty simple. So we use the algorithm of HKP. We say, let's first, for all these EIs, so where EIs are nothing but where the poly basis, you're given copies of rho, just empirically estimate this thing. So empirically estimate trace of EI times rho for all E1 to En. And let's say we get a delta approximation of this. Great, that's first step. The second step is we'd like to solve the following optimization problem. So it's not too hard to show that if supposing EI was trace of, if for example, EI was exactly trace of capital EI times rho mu, and if you solve this following optimization problem, you exactly recover mu. But unfortunately, we don't have access to little EI. We only have access to little EI prime. So there are errors here. So again, little EI was this quantity here, and little EI prime was a delta approximation to this. So we need to solve the optimization problem where little EI was replaced by little EI prime. And the main result showed that if you solve equation 1, if, for example, if you get all the n marginals, or all the n expectation values in step 1, and if you solve the approximate optimization problem for mu prime, you can show that mu minus mu prime in L2 norm is actually small. And this is where the hard part lies. The hard part lies in showing that the log of the partition function is actually strongly convex. But if you have this, if you assume the strong convexity of log partition function for free, then you can show that mu and mu prime is close in L2 distance, but we had to establish that in our work. Right, so this was the algorithm. So actually the algorithm is pretty simple actually, except this technical statement that we had to make in step 3. So let me make a few quick remarks. So first thing, the algorithm is only sample efficient, not time efficient for generic Hamiltonians, even local Hamiltonians. And that's because like we have to solve this optimization problem, which involves the partition function. So Z beta is this trace of e to the minus beta hedge. So it's the partition function. So we don't know how to, it's NP hard to compute the partition function, even approximate it. But for certain class of Hamiltonian and certain temperatures, you can actually show that you can approximate the partition function well, but not generically. And right, yeah. So our algorithm is primarily classical. Like the only step 1 was you given copies of rho, you just need to get measurement statistics, and after that, steps 2 was just a purely classical optimization problem. So given copies of a Gibbs state, obtain these delta expectation values, go back to your lab, solve the classical optimization problem, and you're done. And the final thing is, although our complexity depends exponentially in beta and kappa, we cannot generically hope it to be polynomial in all parameters. The reason is if it was polynomial in all the parameters, then it would actually have a classical complexity theoretic consequence. So it has to be exponential in at least one of the 2 parameters. And it's an interesting question, which parameter it has to be exponential in. Right, so this was learning Gibbs states, and let me go to the final thing. So we're learning stabilizer states. Right, I think in 10 minutes I should be done. So far, like I've spoken about back learning, online learning, all these learning models, and I've always said the sample complexity exponentially better than the Hilbert space in which the quantum state sits. But one fundamental drawback of all these results is time complexity. All these sample complexities are efficient, but the time complexity is bad. So in tomography, shadow tomography, pack learning, learning Gibbs states, in all these learning models, the sample complexity was, sorry, not in tomography, in shadow tomography to the remaining thing, to learning Gibbs states, the sample complexity was very efficient, but it was very time expensive. Like it scaled as d squared, the time complexity, the sample complexity was poly log in d. And this motivates the question, is it possible to time efficiently learn interesting quantum states? And this is a very interesting question. And so the point is, I'm going to be giving some positive results in this direction for stabilizer states. So what's a stabilizer state? So consider first the Clifford circuit. So a circuit consists of Hadamard, the S gate, and the C0 gate, and you can even add in the poly gates. And a stabilizer state is just a Clifford circuit acting on the all 0 input. So all possible, so there's a stabilizer state associated to every Clifford circuit. Just take a Clifford circuit, acted on the all 0 input, you get a stabilizer state as the output. And there are 2 possibilities of learning. The first possibility is given copies of a stabilizer state, what is the stabilizer state? This is kind of like tomography, but for stabilizer states. And the second thing is you want to pack learn stabilizer states. So given P, trace of rho times P, where rho is the stabilizer state, so rank 1 stabilizer state. And you want to learn the stabilizer state in the pack learning setting. And I'm going to be talking about both these things in the next 2 slides. Right. First, let me talk about learning stabilizer states given copies. So there was this very nice result from Montanaro. It was just like a 2-page note. I think maybe it might even have been folklore before that, where you can use Bell sampling to learn stabilizer states. And I'm going to present a slightly alternative view of Bell sampling, which I kind of like. It's called taking derivatives. So, right. And the reason I'm giving you this motivation is because I'm going to go to my final slide. There'll be an open question based on this idea. Right. So every stabilizer state can be written in the following way. So A is just a subspace in F2 to the n. And every stabilizer state is just a superposition over all x in the subspace minus 1 to the degree 2 polynomial x transpose bx times some complex phase to the power linear polynomial s times x. Right. So this every stabilizer state can be written of this form. And I'm going to tell you how to learn these stabilizer states. And for simplicity, I'm just going to assume that the subspace is just the entire Boolean cube, 0, 1 to the n. And there is no complex phase. That just helps my analysis below. Right. Then the goal is to learn this unknown matrix B, because like everything in this state is known to us except this matrix B. So the protocol is pretty simple. Just take 2 copies of psi. These are 2 copies of psi. Let's just write it out. It's just this state because you're going to have 2 copies, x comma y, the phase x transpose bx plus y transpose by times ket x comma ket y. Then I'm just going to perform a simple addition or control not operation between the first and second registers. So I'm going to get x comma x plus y. Nothing happens to the face, only the registers becomes x comma x plus y. Let me then rearrange this summation such that I'm going to call x plus y as z. So the exponent becomes y becomes x plus z now. And now if you observe the exponent, all the summations are happening over F2. So instead of x transpose bx, the x transpose bx in the first sum and the x transpose bx in the second sum are going to get canceled. So you're just going to get a polynomial here. So it's x transpose times some quantity plus z transpose bz. And at this moment, I'm just going to choose to measure the second register. And let's say we got a z tilde, an n-bit string. And if you look at the resulting quantum state, it's just this. Because I've measured the second register, it's just now classical, so it's z tilde. And the superposition is only over the x's. And I can remove the phase out because the phase doesn't depend on x. Now, if I do Bernstein-Maserani, I'm going to just get this quantity because this is a linear function of the exponent. And at this point, I'm almost done. I just took 2 copies of psi. I took a derivative of x transpose bx, a degree 2 polynomial, in the direction of z tilde. And so I took 1 derivative. If I take n such more copies, if I repeat this process n times, I can take n derivatives of a degree 2 polynomial, and that uniquely determines my degree 2 polynomial. And that's it. So I just learned the matrix B, which in turn learns the quantum state psi. So this was using order n copies of a stabilizer state, I can actually learn the stabilizer state. Right. So let me quickly go through what are some other results of stabilizer state before I conclude. So there is pack learning stabilizer states. And in this, again, you're given a uniformly random poly and trace of p times rho. So there was this nice result by Rochedo a few years back where he said polynomial many samples and polynomial in time, you can learn an unknown stabilizer state in the packed learning setting. And the crucial observation that he had in this result was he just observed the trace of p times rho could take integral values, -1, 1, or 0. And based on these integral values, you can actually learn the unknown stabilizer state. There was some work last year, or maybe earlier this year, by Golakata and Liang, where they looked at a slightly different model. They looked at a slightly stronger model of packed learning called the statistical query model. And the statistical query model, it kind of models noise. And they asked, can we learn stabilizer states in the stronger model with noise? I'm not going to define the SQ model because I don't have time. So learners are allowed to make statistical queries to rho. So recall, when I mean by statistical, it kind of gets an estimate of trace of p times rho, but in a slightly weird model, which I'm not going to be talking about now. But what they showed is a very nice, beautiful result. What they showed is they can construct a distribution D, and they show that if you apply depolarizing noise to a stabilizer state, and if you want to learn it in the SQ model, learning these noisy quantum states is as hard as learning parities with noise. And learning parities with noise is a classically, notoriously hard open problem. So they kind of said stabilizer states is easy. Learning noisy stabilizer states in a slightly harder model is going to be hard. So this kind of brings the conundrum, what's really happening to stabilizer states when you add noise to it. And the final thing I'm going to be talking about is this very recent work that happened a couple of weeks back, where they kind of went beyond stabilizer states. So what they showed is, so far we look at stabilizer states are outputs of Clifford circuits. But now let's just say, for example, in addition to Clifford circuits, I add 1 layer of T gates. So we know T gates are hard to simulate. They added 1 layer of T gates, log n many of them, and they showed you can still polynomial time learn this. So this is going beyond stabilizer state framework. And the crucial idea that they had is they just, using this idea of Gossett and Bravi, they, for example, wrote the T state decomposition of the stabilizer decomposition of the T state. And because let's assume the K T states, you're going to get a sum of 3 to the K stabilizer states. And then using some technical modification of Bell sampling, they said you can actually learn Clifford circuits with 1 layer of K T gates, 1 layer consisting of K many T gates. You can learn it in time poly of n, 3 to the K. And if K is log n, this is polynomial time. So the kind of these are the results that actually went from learning stabilizer states to going beyond stabilizer states. Right, a couple of minutes, let me conclude. Right, so there are many open questions. I feel like this field is ripe for research, and there are many, many open questions. So I encourage people to think about these things. And let me quickly tell you some open questions. The first thing is, can we perform tomography efficiently on a quantum computer? So at the moment, the tomography protocol takes d² copies of rho and performs a Shor sampling on it, which we don't know how to implement on a quantum computer efficiently. So can we do it in a time efficient way? which is also sample efficient. In shadow tomography, an important question is, can we remove the n or log d parameter? We don't know how to do that. Can we perform some form of shadow tomography for sparse matrices or low rank matrices? We don't know how to do that. So far, I spoke about packed learning and online learning. There's a version of agnostic learning in classical learning theory. Can we agnostic learn quantum states or even unitaries or channels? Is there even a notion of VC dimension for unitaries and channels? We don't know how to do. We don't know about that. And as I said, stabilizer states is one of the few quantum states that we know how to learn time efficiently. Are there other interesting classes of quantum states that we can also learn time efficiently? I spoke about learning Hamiltonians given copies of a Gibbs state, but the algorithm that I gave inherently produced an L2 approximation of the coefficients. Can we produce an L infinity approximation of the coefficients? We don't know how to do that. And also, can we learn Hamiltonians for a richer class of Hamiltonians in my Hamiltonian learning problem time efficiently? How robust are the algorithms that I proposed so far is with experimental noise in mind. I mean, most of learning quantum states has an experimental background to it. So can we also use this experimental noise models and learn quantum states still in this model? Right, so this is a question which I've been thinking about. It's about, so far I said you can take derivatives of degree 2 polynomials, but can we extend from degree 2 to degree 3 polynomials even? And there's a motivation for looking at degree 3. If you look at IQP circuits, we just see Z, CZ, and CCZ gates. The outputs can be written as just summation over x minus 1 to the degree 3 polynomial in x. So given copies of a degree 3 phase polynomial, can you maybe take multiple derivatives and can you learn outputs of IQP circuits? I think it's a very interesting question. It's something we're thinking about. And finally, this kind of motivates me to the final question. Is there any connection between learning and simulation? So for example, Clifford circuits are simulable, so we can learn the output. IQP circuits are not. So maybe is the output non-learnable, or is there any like fundamental connection between simulation and learning? With that, I thank you for your attention.
Okay, thank you very nice for the nice talk. And now we have some time for questions. So we have already one question. So is there any no lower bounds on shadow tomography?
So in this paper of Arrington and Rothblum, they showed that if you want to do shadow tomography in a private way, there is a lower bound. You cannot get rid of the little n dependence that I have in the second bullet here. But for the non-private setting, I'm not aware of any lower bounds. Mm-hmm. But I think one reference to look at is this paper of Arrington and Rothblum on DP learning, where they give some lower bounds.
Okay, maybe we have some time for more questions. Maybe I can ask one. What about this open problem for finding classes of states which can be learned efficiently? Do you know any candidates for that?
Yeah, that's a good question. Yeah, as far as I know, I mean, I can only think of stabilizer states and some generalization of stabilizer states, but maybe, yeah, I'm not aware of it. Like maybe even like Gibbs states with certain interesting class of Hamiltonians, maybe lattice Hamiltonians, which could be interesting. I know there has been some follow-up work to ours, which talk of time-efficient learning. But yeah, apart from these two things, like Gibbs states of interesting class of Hamiltonians and stabilizer states in the generalization, I'm not aware of any other thing so far.
Okay, thanks. Okay, since we don't have any other question, there is a raised hand by Ana Paula.
Hi, can you hear me?
Yeah.
I think, thank you for your talk, by the way. I think the last question you posed was very interesting. Do you know if there are any connections or something has been made along these lines between connections between learning and simulation?
So there was one result that I'm aware, although I don't think it answers the question that I asked. So there was this result by Mithuna Yoganathan where a couple of years back, she looked at something in these lines, but it still doesn't completely answer the question that I'm asking here. So there was some work like a couple of years back where she looked at ontological quantum states, which have some connection to simulation and learning. But I think the quantum state she learns is still simulable. Yeah, so her work is the only work that I'm aware that kind of has something to do in these lines, but I'm not aware of any other work.
All right, thanks.
Okay. So I guess our time is finished. So thank you very much, and hope you all enjoy the rest of the conference. So see you. Bye.
Thanks. Bye-bye.
Okay, hello everyone. Welcome to the evening session for Tuesday of TQC. The first talk is by Carlos Ortiz Marrero on entanglement-induced barren plateaus. Carlos, if you want to share your slides.
Sure. Just give me 1 second here. And let me just go back here real quick. So thank you very much for the invitation and for allowing me to speak. So for those of you who had a chance to see my talk, so my talk is titled Entanglement-Induced Barren Plateaus. It was joint work with Nathan Wiebe and Maria Kirfova. I won't necessarily repeat all the details that I already laid out in the video, but I thought I might just give you a kind of an overview of the work that we're aiming at conveying or doing, or the things that we're trying to do. So the motivation for this work is, this famous barren plateau phenomena that people in quantum machine learning might be aware of. I just wanted to start with this quote that was just outlining Los Alamos National Lab publication, where the authors claim that this barren plateau phenomena is the key of quantum machine learning. And the motivating question that we were trying to go after is, okay, so what is this phenomena, and how can we fix it? What are some of the things that we could do to address this phenomena? And for those of you who might need a recap, so barren plateau phenomena is this thing that happens when you have a parameterized quantum circuits and you start to increase the number of qubits in your circuits. So what happens is that the gradients with respect to the parameters decay exponentially, which is bad for learning. So one of the things that we did in this work is that we actually showed that the phenomena is actually much worse than originally we expected, because barren plateaus, or this exponential decay in the gradients, occur or can occur from a nexus of entanglement between the visible and the hidden units of your network. So just to give you a recap or an example, so here I have a picture of what we call a quantum neural network, or a unitary quantum neural network with 5 visible units and 3 hidden units. So as what we showed is that if we increase our hidden subspace, and this subspace starts to interact with our visible subspace, then our gradients start to decay just from this entanglement interaction. And just for recap purposes, so by hidden, what we mean is those qubits that at the end of the computation we just throw away, we trace out, we don't really use, and the visible are the ones that we actually do measure. And here's just a quick plot of one of the numerics that you saw in the talk, where we actually managed to show this for small numerical examples. So in the paper, we proved theorems and gave sufficient conditions when this can occur. But we also looked at metrics like fidelity, which we didn't consider in our theorems. And we see that the variance of the gradient, of the norm of the gradient of the fidelity starts to decrease as we increase the number of hidden units in our model. And I also wanted to just talk a little bit about some follow-up work that we did that I couldn't include in my talk, but I thought the people in this audience might be interested. We actually, in our most recent work, showed that we have a way of avoiding some of these barren plateaus by moving from the expectation optimization function to maximally quantum radiant divergence. So that's some work that we published on this paper here, which can be considered as a follow-up to this work. And our paper can be found here at this link. So I think with that, I wanted to maybe stop there and just allow the audience to ask some questions.
Thanks a lot, Carlos. Are there any questions for Carlos? I have one. So you mentioned that the barren plateaus become a problem as you add hidden units or hidden qubits. Is there any relation to the depth of the circuit as well? Like, does it get worse as I increase the number of layers?
Yes, there is some work. I think in our work we showed or we assumed that our circuits were come from a 2 design, which means that the depth is big enough. So we didn't look specifically at that question, but we did use the assumption that our depths need to be deep enough in order for us to prove these results theoretically. Yeah.
So you needed the circuit to form a unitary 2 design.
Yes. Yes. That was a big assumption that we used for, and yeah, there's also, you can have you can assume that your circuit is also modeled by or come from a random or produces a Haar random state. And under that assumption, it also works. But the 2 design assumption allow us to actually prove it for not just the unitary case, but also the quantum Boltzmann machine, which I didn't show it in this picture. But if, for those interested, it's on the talk. There's more details there.
Cool. There's still plenty of time for questions. Are there any other questions for Carlos? I have another one. Can you say a little bit more about?
That's fine. I didn't know how much I wanted to go in depth in these 10 minutes because I wanted to allow people to talk. So my apologies if I went too short. No.
Oh no, that's perfectly fine. Can you say a little bit more about the like switching to the Renyi divergence and what that?
Sure. Yeah. This is something that we put on the archive. We put on archive a couple of days before I had to record a talk, so unfortunately I couldn't put the link in the YouTube video, but I wanted to include this because I didn't want it to forget. So we're very excited about this work. What we managed to show is that we can successfully train circuits like the one that we see here on the right, and also quantum Boltzmann machine if we instead use a Renyi divergence. So in this case, it was the maximally 2 Renyi divergence. And the good thing about using this divergence is that you can actually compute the gradients analytically. And this allows you to do training without having to do approximations. You can get exact gradients. We did also some really nice numerics in that case that allowed us to show that for small numerical examples, you get really, really good training. And we also gave sufficient conditions as to why the barren plateaus are absent using this specific loss function, if you think about it more from a machine learning perspective. And yeah, so if you're interested in hearing sort of a follow-up to the entanglement induced barren plateau talk, that's a great place to go because we also showed that entanglement induced barren plateaus are absent, not just in regular barren plateau phenomena. And the 2 use cases that we decided to showcase our tool were we applied it to the task of learning thermal states and also to the task of Hamiltonian learning. So for those of you interested, please feel free to look at our paper. And if there's any questions, also feel free to send them my way or any of my colleagues. We would be more than happy to answer any questions.
Okay, we're getting close to the 10-minute mark. So thank you, Carlos, for a very interesting talk.
Awesome. Thank you very much, guys.
If you could stop sharing your screen so that Carlo Maria can start sharing.
Yes. Hello, everybody. Let me see. Just a second. I have a small problem with screen sharing. I don't know what's happening.
You're a panelist, right? Yeah.
Yeah.
So you should be able.
Okay. Now it should.
Okay, seems to work. Yeah. So it's 40. So next speaker is Carlo Maria Scandolo from University of Calgary, talking about dynamical entanglement. Please take it away.
Hello, everybody. And I'd like to thank the organizers, first of all, for setting up this conference despite the current difficulties. And it's really my pleasure to be able to speak at this meeting. So, as you see from the title, I'm going to talk about dynamical entanglement in a very concise way. For more details, I invite you to listen and watch my my long talk in the conference website. So this work has been done in collaboration with my colleague Gilad Gur, and it probes entanglement at the level of channels rather than at the level of states. So again, we know that entanglement is a resource because we know that there are the first protocols which explain how to use entanglement to do something useful and something that hadn't been done before. And entanglement is always associated with the idea of spatially separated parties that act locally and then exchange classical communication, which is in this case represented by this dash arrow exchange between Alice and Bob. However, LOCC channels, which are channels that can be constructed in this way, are very hard to study. And therefore, in order to get useful bounds or meaningful results, sometimes it's actually easier to work with another types of channel, which are PPT channels, which are easier to deal with because they are defined in terms of a partial transpose. So we just need to check whether a partial transpose is positive semi-definite. So much easier than essentially examining the structure of the channel. So the reason to study dynamical entanglement is because the first protocols I mentioned, teleportation, dense coding, and so on, transform states, entangled states, into channels, so static resources into dynamical resources. And if we want to manipulate dynamical resources, what we need to consider superchannels. So what is a superchannel? Let's say outside its let's say formal definition, let's talk about its physical realization. In this case, it's realized by this sort of circuit fragment, which is actually called a comb, where there is a pre-processing or encoding and a post-processing or decoding, and then there is a hole where I plug the channel I want to transform. This formalism also allows us to treat states as well. So in other words, we can treat static and dynamical resources on the same ground. So which is good because the first protocols actually do this. So really we do want to study this type of entanglement because this is really the way to study entanglement, because this is the way entanglement was developed as a resource. Now, the interesting thing is that if we take the encoding and the decoding to be free operations in any resource theory, in this case, the resource theory entanglement, for example, LOCC operation, what we get something that we call a freely realizable superchannel. Why is it called freely realizable? Because it can be represented in a laboratory with a free pre-processing and a free post-processing. But now we have the following question, which is still open, at least for the case of entanglement, but in other resource theories even. So is it true that every free superchannel in a resource theory is necessarily freely realizable? So it admits realization in terms of free pre-processing and free post-processing. So that's the main question. And actually, I'll show you very soon that actually, if we don't assume the superchannels involved to be freely realizable, everything becomes simpler. Okay, so let's see what we can do. Clearly, whenever we have a resource theory, we care about the conversion problem. So now, instead of having two bipartite states, we have two bipartite channels, which are channels shared between Alice and Bob with two inputs and two outputs. And we want to see whether we can convert one into another with a freely realizable LOCC superchannel. So here we have the highest complication in the theory because it's freely realizable and also LOCC, so really hard. We can actually at least propose an approach, but then the solution of this approach is actually hard, but which is based on two notions. The first notion is based on the notion of conversion distance. So what do? So we want to convert n into m. Therefore, we apply all possible LOCC superchannels and then to the first channel, so to NAB, and then we want to calculate the distance of the output of this operation to the target channel, and then we optimize over all possible superchannels. And clearly, if this distance is 0, then the conversion can be achieved perfectly. Otherwise, for example, we can fix an epsilon if we want an approximate conversion. And that's one approach. The second approach is actually uses a different technique. So it uses a complete family of entanglement measures. So essentially, this construction is based on convex geometry. So what we do here in this case, so we take any channel in the same systems as the target channel, in this case, P, A prime, B prime. Then J in this expression denotes the Choi matrix. Then what we do, again, we take the Choi matrix of all possible applications of an LOCC superchannel to the original channel N, and multiply with the channel multiply by the Choi matrix of the channel P, which we fix at the very beginning, take this inner product, and then optimize over all possible LOCC channels. And in this way, clearly, this is a complete family because conversion is possible if and only if all the entanglement measures of the initial channel are greater than or equal to the entanglement measure of the final channel for every choice of P. The nice thing is that these two approaches can be recast as conic linear programs, but due to the complexity of LOCC, they are actually hard to solve. So we need to think of something, let's say, more easy to work with. And to this reason, we introduce PPT superchannels. So what are they? So there are various ways to define them. Here I give you the simplest one. So what we do, we take the Choi matrix of the superchannel, which is something that is possible to define. And then essentially the superchannel is PPT. I use Gothic letters here to denote the superchannel as I did in the previous slides. So this is PPT. If I take the partial transpose on both sides, B and B prime, okay, then this is actually greater than or equal to 0. So this is still a positive semi-definite matrix. Okay, so that's the simplest way to define it. For more details, you can see the longer version. Now, that's an interesting thing because this definition is actually easy and powerful because it's given directly at the level of the Choi matrix of the superchannel. We didn't give this constraint on the encoding or decoding of the superchannel. So this is just on the global, if you wish, Choi matrix. So we don't know whether PPT superchannels with this definition are freely realizable. So if there exists a PPT pre-processing and a PPT post-processing that realize that superchannel. But the nice thing of—
Sorry, 2 minutes left.
Okay, yeah, sure. I'm about to finish. So the thing is that both approaches now become SDPs. And again, so what's the message? We can construct simpler measures of entanglement that are easier to deal with and to construct. One example is the negativity. And here, essentially, we use the transpose supermap, which is applying the transpose both at the input and at the output. And then there is another one, which is actually a generalization of the notion of kappa entanglement introduced by Mark Wilde and Xin Wan, and which has a, let's say, more intimidating expression, but it has it gives the exact asymptotic entanglement cost under PPT superchannel. So to summarize, we have entanglement for bipartite channels. We study in particular MPT because it's simpler and it allows us to give easily computable measure of dynamical entanglement. We also found bound entanglement, but there is no time to talk about it now, so please watch the whole video. And then here, of course, there are a lot of open questions. So what can we do in for the general LOCC case? What can we say about multipartite entanglement? And finally, what measures of dynamical entanglement we can construct in this theory? And these are some references. Thank you very much.
Thanks a lot, Carlo Maria. We have time for a quick question. Are there any questions? I have a very quick one. So these entanglement measures, can I think of them as just entanglement witnesses on the level of channels? Is that the idea?
this, you mean the one is the complete family of measures of entanglement? This one?
It's very similar to an entanglement witness, right? Just
Yeah. Formally, because the principle behind it is basically the same. So essentially, you're considering the supporting hyperplanes in this thing, and then you just essentially in this case it's slightly different because there are two things involved here, but the idea is the same essentially.
Okay, nice. Okay, I think we should move on to the next speaker. Thanks a lot, Kalamaria, for this.
Thank you.
Hey, Mark. Good to see you.
Hello.
Do you want to start sharing your slides?
Yeah.
And you're good to go?
Good to go. Should I go?
Yeah, let me introduce you. So the next speaker is Mark Wilde from Louisiana State University, talking about bounding the forward classical capacity of bipartite quantum channels. Please.
All right. Thanks a lot for having us and for chairing the session. And nice to see everyone logged on, some familiar names. So this is a joint work that I did with Dawei or David Ding, Sumi Khatri, Yihue Kwek, who I saw in the audience because she's going to be talking in a few minutes, Peter Shore and Xin Wang. And this was, we had this interest in finding bounds in the classical capacity of quantum channels assisted by classical feedback. I've been kind of pursuing a general research program of trying to understand capacities with feedback for some time now. And we had some earlier results, David, Yihue, Peter, and I, for an entropy bound on classical capacity with feedback. And then Xin had some work where he used like an SDB bound on to get a bound on the classical capacity. And so here we're generalizing that idea to classical capacity with classical feedback. And then while we were doing this, we realized that everything we were doing applied to this more general paradigm of bipartite channels. And so that's how this title came about. All right, what is a bipartite channel? It is a two-party channel where each party has access to an input and an output of the channel, as depicted in this diagram. And yes, indeed. And these systems can be all of different dimensions. It doesn't matter what the local dimensions are. Okay. An example of a bipartite channel would be like a CNOT gate or a swap gate that appear in quantum computation. And if you add noise to them, then they become noisy. Okay. And we're interested in the classical capacity of a bipartite channel. So what is meant by that? Well, let's go back to a point-to-point channel. And here's a diagram that we can use to depict the classical communication scenario for point-to-point. Alice has some classical message that she encodes into a quantum state, and it could be a highly complex multipartite entangled state, for example, that then gets input into some number of uses of the point-to-point channel. Bob receives. In general, he can do a collective measurement and try to decode the classical message that Alice transmitted. And we can think of all the encoding and decoding happening at once. In practice, if you're communicating from Baton Rouge to New Orleans, then you would be using like laser pulses, and the uses of the channel would be spread out over time. Okay, so what is the difference between coding for a bipartite channel and a point-to-point channel? Well, with a bipartite channel, you can have more complex coding strategies that are very interesting and allow for kind of a feedback and adaptive procedures. So now let's suppose that Alice wants to transmit a classical message. She can do a local encoding. On Bob's side, he can send into the channel one share of a state and keep another register of that state as a scratch register in his local quantum computer. And the same for Alice. She can keep this A1 double prime stored in a local quantum computer in principle. Hopefully such computers will be available one day. And then the channel outputs a system for Alice, a system for Bob, and they repeat this. They do these local processing, okay? And it's, you know, the use of the channel is interleaved with local processing. Okay. And then at the end, Bob tries to figure out the message that was sent. So that's the paradigm. What do we do in this work? The main message is that we derived an SDP, a semi-definite program that bounds the classical capacity of bipartite channels. It's pretty known by now that computing the capacity exactly is hard for a point-to-point channel, so it's going to be even more challenging for a bipartite channel. It's not even known whether the classical capacity is computable. That's like a major open question in quantum Shannon theory. So what do we do instead? We bound it with a semi-definite program. This you can evaluate on MATLAB, and it'll run in time polynomial in the product of the local dimensions of the channel. Okay, so the main idea behind the SDP bound is that you know, we're comparing the channel of interest to one that doesn't create entanglement between Alice and Bob, and that's non-signaling from Alice to Bob. You know, so these constraints, when I say doesn't create entanglement, I'm actually referring to NP entanglement, like Carlo Maria talked about in his previous talk. And so the NPT entanglement can be specified by semi-definite constraints, and non-signaling is also a semi-definite constraint. So that's kind of the basic idea. And then in the remaining, I guess, 1 or 2 minutes, I'll talk about just kind of from a high level what these results lead to. So this refers to the classical capacity, and this is a symbol that refers to our upper bound. I'm not telling you what it is yet, but if you evaluate it on a channel called the partial swap channel, this is what you get. So the partial swap channel is specified by this. It's happening in superposition. It's kind of like with probability amplitude 1 minus p. It applies the identity with probability amplitude p. It applies the swap. So if p is equal to 0, the identity is being applied, and that's a product of local identities, and there's no classical capacity there. But if there's a swap, there's a clever strategy you can use that kind of uses superintendence coding and entanglement generation to get 2 bits per channel use. And so our upper bounds interpolates between those 2 extremes, and this is what we found. It's still, we still need to work on figuring out what kind of rate is achievable over this channel. That's the upper bound we find. Okay, how do we get classical communication with classical feedback as a special case? Well, if we change this diagram and we replace every odd use of the bipartite channel with a classical feedback channel, and if we replace every even use of the bipartite channel with a point-to-point channel, then we go from a scheme for communication over a bipartite channel to one for feedback-assisted classical communication over a point-to-point channel. And then it's kind of like the bounds that we derive directly applies. Okay, so this is what you get for the depolarizing channel, the communication rate versus the depolarizing noise parameter. And the blue line is what's achievable, the Halevo information. This red line is our upper bound evaluated. And this is the first known upper bound on the feedback-assisted capacity of the depolarizing channel. At this point, the depolarizing channel becomes entanglement breaking. And so then it's known for entanglement breaking channels that feedback does not increase capacity. So it's like here, there's a sudden jump, our upper bound just collapses to the lower bound. And it kind of suggests that there should be a better upper bound. So that's a future effort question. Let me conclude, and I'm really out of time, just by showing the SDP quantity that's used. This is a semi-definite program that's used in the definition of the upper bound. So this gamma is the Choi operator of the bipartite channel of interest. And then it's kind of like you see that a PPT constraint is involved and a no signaling constraint is involved. And then it's evaluating this infinity norm of the channel, which is of this comparison map And this is telling you like how close this map is to being a channel, like trace preserving. With that, I will stop. Thank you.
Thanks a lot, Mark, for this nice talk. With maybe time for one quick question, if there are any. So in the bound that you just showed on the depolarizing channel, this lower bound is not using any feedback. This is just a Holevin.
That's exactly right. Yeah.
So,
yeah. So it's a good point.
Feedback protocols.
That's a very good point. Could a feedback assisted scheme get you above the lower bound? I don't know. Yeah. I mean, I would expect whatever lower bound you find, it should be continuous, right? And so it should kind of match up with what's going with the point here, and maybe even the derivative should exist, you know. So my thought is that feedback is not going to, if you pin me down and force me to make a choice, my thought is that feedback will not increase the capacity of the polarizing channel. That's the kind of thing we were trying to show, but we couldn't show it.
Interesting. I like that conjecture.
All right.
Okay, I think we should move on to the next speaker. Thanks a lot, Mark, for this nice talk.
Thank you.
And next up is Michael.
Yeah, can you hear me?
You want to start sharing the slides?
Okay. Yeah, can you see my slides?
Yes.
Okay, great.
Okay, so next up is Michael Zurel from the University of British Columbia, if I'm correct.
Yep.
Talking about hidden variable models for universal quantum computation with magic states on qubits. Please take it away.
Okay, thanks. So I'll just summarize our main results briefly, and if anyone wants more details, you can check out the recorded version of the talk on the TQC YouTube channel, or the published version of the talk is down here at this link in the bottom left corner. So first, I'll just summarize the computational model we're interested in. It's quantum computation with magic states. So I'm sure this is familiar to a lot of people, but I'll summarize it anyway. So this is a universal model of quantum computation where you restrict the allowed operations to Clifford gates and Pauli measurements. So these operations by themselves are not universal for quantum computation. Universality is restored in this model through the inclusion of extra non-stabilizer input states that you call magic states. So in the sense, since the operations by themselves are not universal, but with the magic states they are, you can say that the extra computational power of quantum computation is in the magic states. So the key question that we're interested in is this one down here. It's which states are useful for quantum computation with magic states, and what properties give these states their computational power. Because it's not enough to just plug in any state in the input and say, you want computational universality. It's like by the Gauss-Meinel theorem, a stabilizer state wouldn't work, for example. So we want to characterize which states are useful. So one way to approach this question is through quasi-probability representations. There's a ton of these, but this is how this usually works. So as a model with a representation for each of the pieces that goes into quantum computation with magic states, so the states, the Clifford gates, and the Pauli measurements, you start by defining a set of these operators, these A sub alphas. We call these phase point operators. This is how states are represented. So rho is a density matrix representing a quantum state. And you decompose the state in terms of these operators, where these coefficients are real and they add up to 1. So that makes this function W a quasi-probability function. And then the Clifford gates are represented by a deterministic map from phase point operators to other phase point operators. And Pauli measurements are represented by a stochastic map, again, from phase point operators to other phase point operators. And these models lead to a classical simulation algorithm for quantum computation with magic states that applies whenever the quasi-probability function representing the input state is non-negative. So in that case, rather than being a quasi-probability function, it's just a probability distribution, which means you can sample from it. And that's what you do is you sample a phase point operator according to this distribution, and then you just propagate the phase point operator through the circuit, and you return outcomes for the measurements as you go. And this correctly reproduces the predictions of quantum mechanics. But again, this only works when the function representing the input state is non-negative. Now, what we have is a little bit different. So it looks very similar. We call it a hidden variable model for quantum computation with magic states. It looks very similar to the quasi-probability representations. And in fact, the representation of Clifford gates and Pauli measurements is identical. The important difference is the representation of the states. So in our case, rather than being a quasi-probability function, any state can be represented by just a regular probability distribution. So these coefficients are always non-negative and they add up to 1. So here's a nice one-sentence summary of our main result. It's a hidden variable model for universal quantum computation, where all the states, operations, and measurements are represented by regular classical non-negative probabilities. And this also leads to a classical simulation algorithm for quantum computation, just like in the quasi-probability representation case, except in that case, the efficient classical simulation only worked when the input was represented non-negatively. In our case, every state is represented non-negatively. So this means we can simulate any quantum circuit. And there's this question about when is our simulation algorithm efficient? We can simulate any quantum computation, but simulation is generally not efficient. So the question is, how much can we simulate efficiently? We know that for the simulation algorithms based on discrete Wigner functions or quasi-probability representations, the amount of negativity in the representation of the input state quantifies the cost of classical simulation. In our case, we've eliminated negativity altogether, so that's no longer a source of inefficiency, but that just means inefficiency must come from another source. So we know that we can efficiently simulate everything within the scope of the stabilizer formalism. We know that we can simulate some phenomenology beyond the scope of the stabilizer formalism, but exactly how much beyond the scope of the stabilizer formalism is an open question. And that's something we're working on and something we'd very much like to know. But probably to learn more about this question, we'd have to get a better understanding about this polytope on which the model is defined. How much time do I have left?
You have 4 minutes left.
Okay.
5, because you started a little later.
Okay. So I'll just go through an example of what it looks like for 1 qubit. So for 1 qubit, the space of states is just the block sphere, or if you include mixed states, it's the states inside the block sphere as well. The state space of our model is this cube that describes the block sphere. So it has a nice geometrical picture in 1 qubit. It's the same idea for more qubits, except it's higher dimension, so it's harder to visualize. So you just have some space of states, and the state space of our model is some polytope inscribing the space of states. And you associate these phase point operators with the vertices of the polytope. And then we have deterministic update rules for Clifford gates. So under any Clifford gate, vertices of the polytope map deterministically to other vertices. And under Pauli measurements, you get a stochastic map. So under any Pauli measurement, you have with some probability you'll go to one vertex, or some probability you'll go to another vertex. And this is the representation of Pauli measurements. And this is what leads to the classical simulation algorithm for quantum computation. And I think I can stop here for questions.
Thanks a lot, Michael. Are there any questions for him? So this phase space representation, is that just an expansion in the Pauli basis, or do you want to be a little more general here?
It's not just an expansion in the Pauli basis. So there are some quasi-probability representations where these phase point operators do form a basis, but that's not true in our case. So if you want every function to be able to be represented by a non-negative probability distribution, then you need to allow more operators in the set. So we have an overcomplete frame rather than a basis.
Makes sense.
So I can be more specific. The phase point operators are the vertices of the dual of the stabilizer polytope.
I see. There's a question from the audience. Gaurav, you should be able to talk if you unmute yourself. Oh, so he put it in a Q&A. I can just read it out loud.
Sure.
So the question is, if negativity can easily quantify magic, why do we need another representation?
Yeah, so what we're saying is negativity is a necessary condition for quantum computational speedup. It's not so obvious that it's sufficient. So there are other ways to quantify magic, and this is one possible route. Ultimately, we're looking for necessary and sufficient conditions for quantum computational universality in QCM. And this is one route.
But this is
not
not
answers the question.
Yet.
Not established yet, no. So it's hard to talk about efficiency in this simulation algorithm. We can say some things, but not everything. But that's something we're still working on, and probably we'll have to understand more about the structure of the stabilizer. Probably help to say more.
Okay, I hope that answers your question, Gaurav. And let's thank Michael again for a nice talk. And let's move on to the last speaker. Yihui, are you?
Yes, I'm here.
You're there. Great. Do you want to start sharing your slides?
Yeah, just give me 1 second.
Sure.
Okay, you can see my slides now?
Yes.
Okay.
So the last speaker of our session today is Yihui Kwek from Stanford University, talking about a quantum algorithm for PETS recovery channels and pretty good measurements.
Okay, hi guys, my name is Yihui Kwek. I'm a PhD student at Stanford University. And today I'll be talking about how we can implement two very useful theoretical tools in quantum information, namely the PETS recovery channel and the pretty good measurement. And this is based on a paper joined with Andras Gillian, Seth Lloyd, Iman Marvian, and Mark Brody, who you saw just now. So the PETS recovery channel can be understood as the reverse of a quantum channel. What do we mean by reverse? Well, to see this, let's first compare classical channels and quantum channels. So we can think of a classical channel as a conditional probability distribution that maps an alphabet X to an alphabet Y. So the alphabet X is governed by this probability distribution over X. And if you just multiply these two probability distributions, you can get the probability distribution over the output, PY. Now, a quantum channel is very similar, but instead of being a conditional probability distribution, it's a CPTP map. And it maps an input density matrix on the system A, we're going to call this sigma A, to an output density matrix on the system B, and this is omega B. Now, one can ask the question, given these two forward channels, how do we go backwards? What is the reversal channel? And so we all know the answer to this classically. The answer comes from Bayes' theorem, and we can write down P of X given Y if we know basically P of X and P of Y given X. So the input probability distribution and the channel the conditional probability distribution of the channel. Quantumly, there's a very similar kind of object called the PETS map. And this is the quantum, we can think of it as kind of like a quantum reversal channel. So the PETS map is a function of the input density matrix sigma A, which is the quantum analog of Px, and the channel, which is represented by the script n, which is the quantum equivalent of the P of Y given X in the classical case. And you will see that the expression below, which we are going to call the PETS map, it actually reduces to the classical expression on the left-hand side when the input density matrix is diagonal, which means that it's classical, and the channel is a classical channel. So we're going to be focusing on this object, which I've highlighted. And this looks like a very complicated expression, but we're going to actually be able to implement this thing on a quantum computer. So just to provide some motivation, why would we ever want to do that? Well, it turns out that this yellow object is super ubiquitous in quantum information. It appears in recovery, approximate recovery in quantum error correction. It appears as a rate achieving decoder in quantum communication. And it's also part of a subroutine for efficient Gibbs sampling, which is thought to be one of the most promising applications for near-term quantum computers. So the main tool that we're going to use is the quantum singular value transformation. So I'm going to give a short primer on this. So the problem solved by this toolbox is the following. Let's say that I have some matrix, which is n times m, and I want to left multiply a quantum state by that matrix, which means I want to produce a new quantum state, which is proportional to the left multiplication of the original quantum state by A. So why are we interested in this question? Well, it turns out that firstly, this is a very common kind of thing that you would want to achieve in quantum algorithms. And secondly, prior to QSVT, which is the toolbox that we use, there was actually no way to do this for general A. You could also, any way that you could think of was very complicated, and basically our algorithmic tools were very blunt, and too much so for precise error accounting. So if A had in the special case that A is a unitary, it's easy to do this transformation. We just apply the unitary to the quantum state. But if A is non-unitary, non-square, or has large operator norm, then QSVT has an answer to this problem, which is we can achieve this transformation by block encoding A. Block encoding means that we embed A inside a unitary, and then we act with the unitary on not the original quantum state, but an enlarged quantum state. So in this manner, we can still achieve the transformation that I outlined above. And for a pedagogical introduction to this kind of transformation, I would recommend the archive paper that is linked there. So there's a second part to this, which is that not only do we know how to create block encodings, but we also know how to manipulate them. And what this means is that we know a black box quantum circuit that can transform a block encoded U, namely a U that has an A in the top left-hand block, into F tilde of A. And when I say F tilde of A, it means that I'm applying some function F tilde to all the singular values of A. That's why it's called quantum singular value transformation. And this method works for F tilde being a polynomial. And by the way, A is typically some object of interest. In our case, we're going to take A to be some density matrix. So the typical use case is that we want to transform A by some function which may not necessarily be a polynomial, but then we just choose F tilde to be a polynomial approximation to the desired function. So let's look back again at our expression for the PETS recovery map, which we want to implement. We're going to need to block encode density matrices, like I said, and we're going to need to apply the function fx equals to x to the half and fx equals x to the minus half. Okay, so we have an algorithm that actually does all of that. For the actual details, I refer you to my talk. So what's the upshot? The upshot is that if we are given a unitary that implements an isometric extension of the forward map, remember we're interested in doing the reversal map, then for the PETS map of n and sigma is the default input state to the forward map, we can actually implement this using our algorithm with square root of dE kappa n sigma uses of u n. Okay, so what are these parameters? dE is the environment dimension, which we defined more carefully in our paper, but we can think of it as at least the Krauss rank of n. And the Krauss rank of the forward map is something like a measure of complexity of the forward map. So it kind of makes sense that the more complex the forward map is, the harder it should be to implement the reverse map. So that's why this parameter appears there. And the second parameter is kappa. Kappa is condition number. Condition number is something that comes from numerical linear algebra, classical numerical linear algebra, and it's a measure of how difficult an object is to invert. And the condition number is defined as 1 over the minimum singular value of that object. In this case, the object is n sigma A. So it's the default output state of the channel. Okay, so that's the main result. And as an application, we can also implement pretty good measurements. Now, pretty good measurements are also a ubiquitous tool in quantum information. They actually allow you to do almost optimal state discrimination for more than or equal to 3 states. And the reason why we can do so using our algorithm is that the pretty good measurements turn out to be a special case of the PETS map. We have an algorithm for implementing the PETS map, and therefore we have an algorithm for implementing pretty good measurements. So that's all I wanted to say. So just to summarize what we presented, we now have a quantum algorithm that is able to implement these 2 ubiquitous QI tools in a systematic and rigorous fashion. It's pretty close to optimal in gate complexity. And I didn't really mention this just now, but it's a neat argument which uses the Grover search lower bound. And lastly, we hope that our new implementation can bring these tools that previously existed in theory closer to implementation on an error-corrected quantum computer. So that's all. Thank you.
Thanks a lot, Joel, for a very nice talk. We have time for questions. Don't see any yet. Can you, I have a quick one about the block encoding for the single value transformation. If you can go back to that slide.
This one or the previous one?
One more, I think, back.
Yeah.
Yeah. What is the significance of this alpha here? Is this?
Ah, yes. Okay. So if you want, okay. So if you look at the top left-hand block of the unitary, the operator norm of that block has to be less than 1. So in cases where you care about implementing the transformation where A has operator norm greater than 1, you then have to subdivide, well, you have to divide all of its entries by the operator norm of A in order to put it inside this like top left-hand block of the unitary. So that's why
this is a necessary condition for a unitary, I guess. That
yes, it's a necessary condition for a
unitary. One, right? Okay. But it's not. So this is not to kind of like avoid any numerical instabilities or something. It's literally just so that you can do this unitary encoding of the operator.
Yes.
Right.
But actually, we'll see that, or actually in our paper we have that when you have the division by alpha, that actually kind of like makes the like resulting A psi like more difficult to recover. So you have to kind of like do some kind of amplitude amplification procedure in order to like get rid of the alpha.
Okay, interesting. Okay. Any more questions for you? If not, then thank you very much for your nice talk, and thanks to all the speakers of the session. And so this concludes the session, and TQC will return tomorrow at 10 a.m. Latvian time. Have a good night or a nice day, depending on where you are.